What happened before the Big Bang? No question stretches the boundaries of human thought quite like this one. What happened before the Big Bang? The very idea invites the mind to journey beyond time itself, into a realm with no clocks, no stars, no form, only mystery. Scientists often remind us that the Big Bang wasn't an explosion in space, but an explosion of space. Time, matter, and energy all sprang into existence at that moment, which means that the phrase "before the Big Bang" might not even make sense in the way we're used to. If time itself was born in that cosmic moment, can anything actually be said to have come before it? Still, the question persists, echoing in our deepest philosophical and scientific curiosities. If there was truly nothing, how did something arise? And if there was something, what was it? Imagine staring into a blank canvas, not just white, but truly absent of anything. No light, no shadow, not even the potential for a brush stroke. This is the kind of nothing many imagine existed before the universe, but the concept of nothing is slippery. Is nothing the absence of particles? The absence of space? The absence of time? Or is it something more nuanced? A potential field waiting to be stirred? Some physicists propose that quantum mechanics allows particles to pop into existence even in a vacuum, so even nothing might be more something than we think. The vacuum isn't empty in the way a box without marbles is empty. It's a restless, energetic field, full of possibility. Could our universe have emerged from such a seething, fluctuating quantum vacuum? Others suggest the universe was born from a singularity, a point of infinite density and temperature, where all physical laws break down. But this isn't something we can probe directly. Our current understanding of physics, specifically general relativity and quantum mechanics, collapses under those conditions. It's like trying to describe the center of a tornado by studying a leaf caught in the wind. At best, we can make educated guesses. One such guess is that before the Big Bang, there was a previous universe that collapsed in on itself, a big crunch that preceded our own expansion. If this were true, the Big Bang wasn't a beginning, but a transition, a rebirth in an eternal cycle. This cyclical universe model has a haunting elegance. It echoes ancient ideas found in Eastern philosophies and myths, endless cycles of creation and destruction, of time turning like a wheel. In modern physics, such ideas have been explored in models like the ekpyrotic universe, where our Big Bang was triggered by the collision of two higher dimensional brains in a multiverse. In this scenario, our universe is just one sheet in a higher dimensional space, and periodic interactions with neighboring brains cause cycles of expansion and contraction. What seems like the beginning may simply be a breath in an infinite lung. Then there's the idea that the universe began as a quantum fluctuation. This theory suggests that out of a quantum vacuum, a frothy sea of uncertainty and potential, our entire universe could have simply blinked into being. According to this model, the laws of quantum mechanics allow, even necessitate, that energy can briefly borrow existence, sprouting entire particles and maybe even universes before vanishing again. If the fluctuation is just right, it might not vanish, it might expand, like ours did. But then we must ask, if this vacuum gave birth to everything, where did it come from? Can quantum fields exist outside time, outside space? Or is this just shifting the question to a deeper level? Another contender is the multiverse hypothesis. Maybe our universe is just one of many, bubbling up in an eternal inflationary field. Imagine an infinite foam, with each bubble representing a separate universe, each with its own laws, dimensions, and timelines. Some pop quickly, others expand forever. In this view, the Big Bang is just our bubble's birth, not a universal beginning, but a local one. Some theories even suggest that universes can be born from black holes in other universes, like cosmic seeds being scattered across reality. In this recursive scenario, one universe gives rise to another, and so on, indefinitely. But again, we are left wondering, what is the source of the foam? Others prefer to dive even deeper, proposing that time itself is an illusion. Physicist Julian Barbour suggests that what we perceive as time is just the way our brains interpret sequences of static configurations. In this timeless view, the universe didn't begin, it just is. Every moment exists simultaneously, like frames on a reel of film. Our sense of progression is an artifact of consciousness. If time never truly flowed, then before the Big Bang is as meaningless as asking, what's north of the North Pole? There may not have been a before, because there was no time in which before could exist. Still others speculate that we live in a simulation. Perhaps what we call the Big Bang was not a cosmic explosion, but the booting up of a system, a switch flipped in some higher order consciousness or advanced civilization. To them, it may not have been dramatic at all, just another program launch. If this is true, then asking what came before the Big Bang is like asking what your video game character sees when the game is off. The answer may be nothing, because you only exist when the system is running. The framework outside the simulation is beyond our comprehension. It exists in a different plane of logic entirely. And yet, despite all these mind-bending possibilities, we must admit a humbling truth: we do not know. And perhaps we never will. The veil before the Big Bang may be one science can never pierce, not because it is impossible in principle, but because our tools, our minds, and even our language may be forever confined within this universe's boundaries. Time and space are the stage on which our thoughts play. To reach behind the curtain is to leave the stage entirely. What lies beyond may not be describable in terms we can grasp. It may not be describable at all. Philosophically, this touches on the limits of human cognition. Every theory, every model is still a product of minds embedded in time. Can the fish truly understand the ocean's birth? Can a shadow understand the flame that casts it? In trying to look beyond the Big Bang, we may be like children standing at the edge of a vast, silent forest, sensing only echoes of something deeper. Our curiosity is boundless, but our perspective is small. The mystery may remain, not as a flaw in knowledge, but as a sign of how precious and wondrous the known truly is. And yet the very act of wondering lifts us beyond the physical. To ask what came before the Big Bang is to stretch the mind into realms without boundaries. Whether the answer is found in equations, in dreams, or never at all, the question itself reshapes how we see everything. It reminds us that existence is not a given, that everything we touch, feel, and remember may be the echo of something far more mysterious. It humbles us and awakens us. It says, "Here you are, alive inside a story that may never be fully told." And what a story it is! What is the ultimate fate of the universe? When we gaze into the night sky, we often feel a sense of awe. Billions of galaxies shimmering like grains of sand scattered across a dark ocean. But hidden behind the beauty of the cosmos is a quiet, unsettling truth. It will not last forever. Just as stars are born, burn brightly, and eventually die, so too will the universe. Everything we know, every galaxy, every atom, every fleeting moment of time is part of a story with an end. But how that end arrives remains one of the greatest mysteries in science. Will the universe fade into silence, tear itself apart, or collapse in on itself in a final breath? The possibilities stretch as far as space itself. The most widely discussed scenario is the Big Freeze, also known as heat death. It is perhaps the quietest of endings, but no less chilling in its implications. In this vision, the universe continues to expand forever. Galaxies drift farther and farther apart, their light redshifting into darkness. Star formation ceases. Existing stars exhaust their nuclear fuel, becoming cold white dwarfs, then black dwarfs, and eventually disappearing into the blackness. Over time, even black holes evaporate via Hawking radiation, dissolving into nothing but faint heat. What remains is a dark, featureless void. No stars, no planets, no light. Just particles spread thinly across unimaginable distances, trapped in a frozen and entropic silence. A universe that never ends, but is as good as dead. But the Big Freeze is not the only possible ending. Some scientists propose a more dramatic finale, the Big Rip. In this model, a mysterious force known as dark energy doesn't just push galaxies apart, it grows stronger over time. Eventually, it begins to tear gravitational bonds, separating galaxies, then solar systems, then planets from stars. As the repulsive force grows unchecked, it overcomes the forces that hold matter together. Even atoms are ripped apart. Space-time itself unravels in a final, catastrophic moment. The universe does not freeze, but shatters, destroyed from within by the very expansion that gave it birth. If this is our destiny, the cosmos will end not with a whimper, but with a scream. Yet another possibility is the Big Crunch. In contrast to expansion, this theory imagines a reversal. If the total amount of matter and energy in the universe is sufficient, gravity may eventually halt the expansion and begin to pull everything back together. Galaxies will slow their outward journey, the universe will contract, space will shrink, temperatures will rise, stars and galaxies will collide, black holes will merge. Eventually, all matter and energy collapse into a dense singularity, a mirror image of the Big Bang. Perhaps this leads to a new universe, perhaps not. But either way, everything we know would be crushed into oblivion. The clock winds down and then snaps shut. Still, some scientists consider a more subtle, unsettling outcome: vacuum decay. This scenario is rooted in quantum mechanics and the strange nature of what we call the vacuum, the apparent emptiness of space. According to this theory, the universe may not be in its most stable state. Instead, it could be in what physicists call a false vacuum, a temporary metastable state. If a more stable configuration exists, then a quantum event could trigger a sudden transition, like a bubble popping in a sea of potential. A new vacuum state could emerge and expand at the speed of light, erasing the laws of physics as we know them. No warning, no escape. One moment everything is as it was. The next, it simply isn't. Each of these endings, freeze, rip, crunch, decay, emerges from equations and theories we understand today. But the future of the universe depends on many things we still do not fully grasp. What is dark energy truly? Is it constant, or does it evolve? Will it decay? Is our understanding of gravity complete? Could quantum gravity, the theory that unites the very large and the very small, reveal new forces or dimensions. Our best models are limited by the boundaries of current knowledge. The universe may yet surprise us. There could be endings beyond imagining, timelines in which the cosmos recycles, splits, resets, or transforms into something altogether new. There are even models in which the universe ends in a rebirth. The so-called bounce theories suggest that rather than reaching a singularity and ending, the universe may rebound, with each big crunch leading to a new big bang, a perpetual cycle, a cosmic heartbeat. Time itself could be circular, with universes giving birth to other universes in an endless loop. These ideas find echoes in ancient myths, of phoenixes rising from ashes, of eternal return. In modern physics, they are explored through ideas like loop quantum gravity and string theory. If true, then this universe may be one chapter in a book with infinite pages. But we should also reflect on what any of these endings mean for us. As individuals, we live for decades. As civilizations, perhaps for millennia. The universe moves on timescales that dwarf our minds. The Big Freeze, for example, unfolds over trillions upon trillions of years. Stars that shine today will be long gone. Our sun will burn out in a mere 5 billion years. Entire galaxies may fade before the real darkness begins. If we vanish tomorrow or spread to the stars, the universe will still proceed toward its end, patiently, indifferently. We are witnesses to a process that began billions of years ago and will echo long after we are gone. And yet this knowledge does not have to be bleak. Knowing the universe will end is also a reminder of how rare and precious our moment is. The stars still shine. The earth still spins. We exist during a cosmic spring, a time when galaxies are still visible, when life can flourish, when meaning can still be made. To be alive now, with minds capable of wondering about the end of time, is extraordinary. We are children of stardust pondering the death of stars, consciousness reflecting on the abyss. That is no small thing. Some thinkers have gone further, wondering whether consciousness itself plays a role in the universe's fate. If reality only fully exists when observed, what happens when there are no more observers? Does the universe freeze, not just physically, but perceptually? These are speculative thoughts, drifting into philosophy, but they point to a deeper yearning, the wish that something of us might last, that awareness might continue, that in the end, the universe will not be empty, but illuminated from within by something enduring. And then there are those who believe that perhaps there is no final end, only change. Just as a caterpillar becomes a butterfly, the universe might transform into something wholly new when its current form reaches exhaustion. What seems like death may be metamorphosis. The fabric of reality might bend into another dimension, another form of existence. Perhaps energy becomes thought. Perhaps space becomes silence. Perhaps we awaken somewhere else entirely, beyond the reach of our current physics, in realms unbound by light or time. Still, for now we live in the middle chapters. We see the traces of the beginning, the echo of the Big Bang in the cosmic microwave background, the inflation that shaped galaxies, the fusion that forged elements in stars. We walk through a world carved by ancient forces, beneath skies lit by distant suns, and we wonder, where does this road go? What lies at the end? Is it a quiet freeze, a violent rip, a crushing collapse, or an unseen transition? Whatever the truth may be, it reminds us that everything is temporary, that change is the only constant, even on cosmic scales. And in that awareness lies both humility and purpose. We are not eternal, but we are here, for now. And maybe that's all that matters. To see, to know, to feel. To ask questions whose answers may never come, and to love the asking all the same. What is dark matter? When we look up at the night sky, we see stars, planets, and galaxies, brilliant islands of light suspended in a sea of darkness. But what if the things we see, the glittering matter that makes up everything from stars to our own bodies, are just a small fraction of what's really out there? According to modern cosmology, all the atoms, dust, and radiation that we observe account for less than 5% of the total mass and energy of the universe. Roughly 27% is something far more elusive: dark matter. It doesn't shine. It doesn't absorb light. We cannot touch it, or see it, or capture it in a lab. And yet, it's there, bending galaxies, shaping the cosmos, whispering to us in the language of gravity. It is a ghostly presence, embedded in the universe's very bones. So what is dark matter? At the most basic level, it's a term we use for whatever is causing the gravitational effects we observe but can't explain with visible matter alone. In the 1930 Swiss astronomer Fritz Zwicky was the first to notice something strange. While studying galaxy clusters, he found that galaxies were moving much faster than expected. Based on the amount of visible matter, they should have flown apart, but they didn't. It was as if some hidden mass, something invisible, was binding them together. He called this unseen glue dunkle Materie, dark matter. For decades, his idea was largely dismissed. But in the 1970s, Vera Rubin's studies of spiral galaxies confirmed something profound. Stars at the edges of galaxies were moving just as fast as those near the center. According to Newtonian physics, this made no sense unless something invisible was creating extra gravity. And so, dark matter stepped out of the shadows. Today, dark matter is no longer a fringe idea. It is a cornerstone of modern astrophysics and cosmology. It explains why galaxies hold together, why galaxy clusters behave the way they do, and even why the large-scale structure of the universe looks like an intricate cosmic web. Imagine a scaffolding of unseen mass stretching across the cosmos, dictating where galaxies form, how they grow, and how they move. We can't see this scaffolding, but we can see how galaxies cling to it, like dew on a spider's web. Computer simulations of the early universe show that without dark matter, galaxies wouldn't have had enough time to form. The universe would be a very different place. Perhaps lifeless, perhaps unrecognizable. But despite all the evidence for its existence, we don't know what dark matter is. This is one of the most haunting scientific mysteries of our time. We know it's not made of the same stuff as ordinary matter, protons, neutrons, and electrons, because it doesn't interact with light or the electromagnetic force. It doesn't emit, absorb, or reflect radiation. That's why it's dark. But it does have mass. It exerts gravity. It holds galaxies together and tugs on the fabric of space. So what could it be? One possibility is that dark matter is made up of yet undiscovered particles. Physicists have proposed a zoo of candidates: WIMPs, axions, stereoneutrinos, each with different properties and behaviors. These particles would be invisible to our detectors, but they might leave subtle signatures in cosmic radiation or in the distribution of galaxies. WIMPs, weakly interacting massive particles, were once the leading candidates. These hypothetical particles would be heavy, like protons, but barely interact with ordinary matter. If WIMPs exist, they should occasionally collide with atomic nuclei, releasing tiny bursts of energy. To detect these faint collisions, scientists have built elaborate underground detectors, shielded from cosmic rays and natural radiation. These detectors are buried in abandoned mines, deep beneath mountains, in ultra-pure chambers of liquid xenon or argon. Every now and then, a faint flash might hint at a WIMP brushing past, but so far no definitive detection has been made. The silence in these detectors is deafening. It forces scientists to reconsider, refine, and imagine other possibilities. Another candidate is the axion, a lightweight particle that could be all around us, like a vast ocean of invisible mist. Axions are expected to interact with magnetic fields in very specific ways, and physicists have devised clever experiments to detect these effects. Still, nothing conclusive has emerged. And then there are sterile neutrinos, ghostly cousins of ordinary neutrinos, which barely interact with anything at all. If these particles exist, they could be drifting through our bodies right now, unnoticed. But again, the evidence remains elusive. It's like trying to solve a puzzle when most of the pieces are missing, and you're not even sure what the final picture is supposed to look like. Some scientists have even begun to wonder whether dark matter exists at all, or whether our understanding of gravity itself is incomplete. Perhaps the laws we use to describe the cosmos, like Newton's and Einstein's equations, break down on large scales. Modified gravity theories, like Mond or Tve's, suggest that what we interpret as dark matter might instead be the result of gravity behaving differently than we expect. These ideas are bold, and they face challenges in explaining all the observed data, especially the patterns in the cosmic microwave background and galaxy distribution. But they remind us of an important truth. Science thrives on doubt, on the willingness to question even the most sacred equations. There's also the idea that dark matter might not be made of particles at all. What if it's composed of primordial black holes? These would be tiny black holes formed in the very early universe, long before stars or galaxies. If they exist in the right abundance and mass, they could account for dark matter's gravitational effects. But recent studies suggest they're unlikely to make up all of it. Other theories propose dark matter as a field, like a fog filling all of space, fluctuating gently across the cosmos. Some ideas are so strange they border on science fiction. Dark matter might exist in its own shadow universe, with shadow atoms and shadow stars, forever hidden yet gravitationally intertwined with ours. And so the search continues. Around the world, physicists, astronomers, and cosmologists build ever more sensitive detectors, launch new telescopes, and refine their models. They listen to the cosmos with instruments that can detect gravitational waves, map dark energy, or catch a glimpse of high-energy cosmic particles. Each experiment, whether it finds something or not, brings us closer to the truth. But it is a slow, patient journey. Dark matter does not reveal its secrets easily. It surrounds us, shapes us, but remains invisible. It is the scaffolding of galaxies, the silent partner in cosmic evolution, the unseen architect of structure. In a strange way, dark matter humbles us. It reminds us that most of the universe is hidden, that our senses, our eyes, our instruments, even our imagination, capture only a sliver of reality. We walk through a world built on shadow, and yet we keep searching because that's what we do. We ask questions that seem impossible. We imagine things we cannot see. And sometimes, we find light in the dark. Perhaps one day we will hold a piece of dark matter in our hands. Perhaps we will understand the true nature of this cosmic ghost, Or perhaps, like so many mysteries, it will continue to dance just beyond our reach, drawing us ever forward into the unknown. Why is there something rather than nothing? Among all the questions that human beings have ever asked, one towers quietly above the rest. It is not concerned with how stars burn or why apples fall, not even with how the universe began or how it might end. It asks something even more basic. Why is there anything at all? Why is there something, matter, energy, space, time, thought, instead of absolutely nothing? Why does existence exist? It is a question so simple that a child can ask it, yet so deep that no philosopher or physicist has ever truly answered it. It is the riddle of being itself. A silent whisper beneath every discovery and every observation we make. Something is here, but why? To begin to explore this question, we must understand what we mean by nothing. It sounds obvious, nothing is the absence of everything, but when we truly consider it, the concept becomes slippery. Is nothing the absence of matter, or the absence of space, of time, of laws? Can nothing be said to exist at all, or is it just a linguistic placeholder for something we can't actually imagine? Some thinkers argue that the very idea of nothing is incoherent. If we try to conceive of absolute nothingness, a reality with no time, no space, no fields, no logic, what we end up picturing is still something. A dark void, a blank canvas. But even that is structure. Even that has form. Can we ever truly think nothing? Philosophers have wrestled with this enigma for centuries. Leibniz, in the 18th century, famously posed the question in its modern form, why is there something rather than nothing? For him, the existence of anything at all demanded a reason. He argued that the best explanation was a necessary being, something that exists by its own nature, something that could not exist. To Leibniz, this necessary being was God, and from that divine necessity flowed all contingent things. But others have challenged this view. Is the notion of a necessary being coherent? Could the universe itself be necessary? Or might existence arise without a reason at all? In modern times, physics has entered the conversation. Some scientists suggest that the laws of quantum mechanics allow for the spontaneous emergence of a universe from nothing. According to this view, the vacuum is not empty in the classical sense, but a bubbling sea of quantum potential. Particles appear and vanish all the time. Under certain conditions, entire universes might do the same. If this is true, then perhaps nothing is unstable. Perhaps, given the laws of physics, something must emerge. But this raises its own profound question. Where did the laws of physics come from? Are they eternal? Did they exist in the absence of space and time? And if they did, is that truly nothing? Cosmologist Lawrence Krauss has argued that a universe can arise from nothing, in the sense of a quantum vacuum governed by physical laws. But critics point out that this vacuum isn't really nothing. It's a structured, law-filled field. And even if such a model explains how a universe could arise, it doesn't tell us why there is a vacuum, or laws, or the possibility of existence in the first place. We push the question back a step, but it never disappears. Like a shadow that stretches as we chase it, the mystery recedes with every attempt to grasp it. Why should there be laws at all, rather than lawlessness or silence? Another possibility is that there is no reason, that existence is simply brute fact. It just is. No cause, no explanation, just being. Some philosophers find this unsatisfying, while others accept it with a kind of reverence. If there is no ultimate explanation, perhaps the mystery is not meant to be solved, but embraced. Maybe the very act of questioning brings us closer to something real, even if the answer lies forever beyond our reach. As the poet Rainer Maria Rilke once wrote, "Live the questions now." Perhaps the most honest approach is to sit in the mystery, letting it expand within us like a deep breath held in silence. There's also the intriguing idea that nothingness is less stable than being. Some cosmologists suggest that in the realm of quantum physics, a true vacuum is not the default, but an unstable anomaly. Given enough time, or no time at all, it may inevitably erupt into existence. In this view, the creation of something is not a miracle, but a statistical necessity. Existence happens not because it was designed or needed or willed, but because it could not happen. But again, we're faced with a haunting question. What permits possibility? Why is there any potential at all? Why is the landscape of existence shaped in such a way that something is allowed to emerge? And then there is consciousness, the part of the universe that reflects, questions, and wonders. Perhaps the strangest thing about reality is not that it exists, but that we are here to notice. Why should particles arrange themselves into thinking beings? Why should the cosmos become aware of itself? Is the presence of observers of minds a clue to the mystery? Some theories, like the anthropic principle, suggest that the universe must be as it is because otherwise we wouldn't be here to observe it, but this is more of a tautology than an explanation. It tells us why we see something rather than nothing, but not why there is something to see. In Eastern philosophy, especially in traditions like Taoism and Buddhism, the question of being and non-being is approached from a different angle. Rather than framing it as a puzzle to be solved, it is seen as a dance, a balance. Being and non-being are not opposites, but complements. Form arises from emptiness and returns to it. The Tao Te Ching says, "We shape clay into a pot, but it is the emptiness inside that makes it useful." In this way of thinking, nothing is not the enemy of something, but its partner. Perhaps the universe is not a mistake in the void, but an expression of it. Some thinkers propose a multiverse, a landscape of countless universes, each with its own laws and parameters. In such a scenario, universes arise constantly, and we just happen to live in one capable of supporting complexity. But even here, we are left wondering, why is there a multiverse? Why is there a mechanism for universes at all? The scale changes, but the question remains. Whether it is one universe or many, we are still faced with the original mystery. Why anything? And perhaps the most provocative idea of all, maybe the question itself is flawed. Maybe nothing is not the natural state. Maybe we only think it is because we are beings used to beginnings and endings. We assume that absence is simpler than presence, that zero is more natural than one. But what if existence is the base state? What if it's the only game in town? From that perspective, the real question might not be why is there something, but how could there not be? Perhaps existence, strange and chaotic and vast as it is the most fundamental fact of all. But still, the mystery remains. It haunts the minds of philosophers, scientists, poets, and ordinary people who stare into the night sky and feel a strange pull toward the unknown. It is not just a question of physics or theology or metaphysics. It is a question of wonder. Why is there something rather than nothing? Why are we here? Why is anything here? Perhaps the answer will one day emerge from the equations, or from some future theory of everything, or perhaps the question will remain forever open, like a doorway that never closes, inviting each new generation to step through into deeper reflection. And maybe in the end, the mystery itself is the gift. The fact that we can even ask this question, that we can feel its weight, its beauty, its silence, is evidence of something extraordinary. That in a universe of stars and dust, life has arisen that not only sees but yearns to understand. That we, fleeting and fragile, are touched by a question as vast as time itself. There may be no final answer, but perhaps the asking is enough. What is time, and why does it flow in one direction? Time is the invisible thread that holds our lives together. We are born, we grow, we age, we die, all carried along by this unseen current that seems to flow ever forward. Every second that passes feels irreversible. We remember the past, experience the present, and anticipate the future. But what exactly is time? Is it a fundamental part of the universe, woven into the fabric of reality? Or is it simply a construct of the human mind, a way for us to make sense of change? For all our scientific advances, the nature of time, and especially the reason it flows in one direction, remains one of the deepest and most baffling mysteries we have yet to unravel. At first glance, time seems obvious. It's what clocks measure. It's what separates one moment from the next. But when physicists look closely at the fundamental laws of nature, something strange happens. Those laws, whether from classical mechanics, quantum theory, or even general relativity, are mostly time-symmetric. That means they don't care whether time moves forward or backward. The equations work the same either way. You could play the tape of the universe in reverse and the laws would still make sense. Yet we don't experience time like that. We never see broken glasses unbreak. We don't grow younger. Memories flow in one direction. Why? This discrepancy is known as the arrow of time. While the laws of physics are neutral about direction, our everyday experience screams of a one-way flow from past to future. So where does that arrow come from? The most widely accepted answer lies in a single profound idea: entropy. Entropy is a measure of disorder. According to the second law of thermodynamics, in a closed system, entropy tends to increase over time. Order gives way to chaos. Hot things cool down, buildings crumble, eggs break. And once disorder increases, it's extremely unlikely for things to spontaneously go back. That's why we remember the past, when entropy was lower, and not the future, when it will be higher. This idea that the arrow of time is really the arrow of increasing entropy explains much of what we see, but it raises a haunting new question. Why was the universe so low in entropy to begin with? After all, if disorder is more probable than order, why did the cosmos start in such an incredibly ordered state? The early universe, shortly after the Big Bang, was hot and uniform, conditions that correspond to low entropy. That smooth beginning is what allows entropy to increase and time to have a direction. But where did that smoothness come from? Why didn't the universe begin in a more random, chaotic state? We don't know. And that ignorance cuts to the heart of the mystery. Some scientists believe that the answer might lie in the structure of space-time itself. In Einstein's theory of general relativity, time is not a separate entity but part of a unified four-dimensional fabric known as space-time. Just as we can move freely through space, time is treated as another dimension, one we travel through inexorably. In this framework, all moments, past, present, and future, are equally real. This idea is sometimes called the block universe view. From this perspective, the flow of time is an illusion. All events already exist. We only experience them sequentially because of how our minds are wired. The universe doesn't change, we do. But this still doesn't explain why we perceive time flowing in one direction. If all moments are equally real, why do we remember the past but not the future? Why do causes precede effects and not the other way around? Some suggest that consciousness itself is tied to entropy, that the arrow of time is intimately linked to how information is processed in brains. As we move from lower to higher entropy, we gain information about the past and lose access to the future. Our sense of flow may not be a property of the universe, but of the observer. Others turn to cosmology for answers. Perhaps time's arrow is born in the very shape of the universe's life cycle. If the universe began with a big bang and ends in a big crunch or some final collapse, then maybe time has a global direction. But what if the universe expands forever, in a slow fade toward heat death? Some theories suggest that even in a freezing, expanding cosmos, entropy still rules, and time flows forward. Yet others speculate that time may reverse in a contracting universe. In such models, people in the distant future might experience time running backward, although that would be indistinguishable from our own forward flow, from their point of view. Quantum mechanics adds further layers of complexity. At the smallest scales, particles behave in ways that defy classical intuition. In some interpretations of quantum theory, like the many worlds hypothesis, every possible outcome of a quantum event actually occurs in a branching multiverse. Each branch has its own timeline, and time flows only within those branches. In other interpretations, like the transactional model, events in the future can influence the past through backward in time signals. These ideas remain speculative, but they challenge our most basic assumptions about causality and temporal flow. Could the arrow of time be an emergent property, not fundamental at all? Some researchers have proposed that time itself is not real, that it's an illusion generated by change. This idea is echoed in the work of physicist Julian Barbour, who suggests that all that exists are configurations of the universe, snapshots, or nows. What we perceive as the passage of time is just the succession of different nows, strung together by memory and causality. From this viewpoint, there is no river of time, only stillness, only a landscape of moments like frames of a film, each existing eternally in its own right. Our experience of flow is the illusion of movement across these frames. Still others point to the role of initial conditions. Maybe the arrow of time is not something fundamental, but something that depends entirely on how the universe began. If that's the case, then we may be stuck with it. We can study entropy, we can model thermodynamic systems, but the reason the universe started low in entropy might be buried forever in the earliest, unreachable moments of the Big Bang. It may be like asking why a story begins on page 1. That's just how stories are told. But there's something poetic, even beautiful, in our experience of time. Its one-way flow gives life shape. Without time's arrow, there would be no memory, no growth, no decay, no meaning. We would not strive, we would not change. Time gives us the arc of a life, the tension of a journey, the poignancy of endings. It makes every moment finite and therefore precious. The fact that we don't understand time doesn't make it any less real to us. If anything, it makes it more mysterious. We live inside something we can't define, carried forward by a current we cannot see. And so we continue to ask, what is time really? Is it a dimension, a direction, a human invention? Is it born from entropy, or from quantum probabilities, or from something even deeper? We do not yet know. But in asking, we deepen our understanding of ourselves. We are beings who live in time, shaped by it, haunted by it, and though we can't stop it and don't fully understand it, we can cherish it. We can fill it with wonder, with thought, with love. Perhaps the ultimate secret of time lies not in its mechanics, but in its mystery. That even if physics finds an equation or a model or a theory, the experience of time, its flow, its passing, its meaning, will always be personal, intimate, and profound. We are not just creatures of space, but of time, and in that fleeting passage from moment to moment, we find our stories, our hopes, our lives. What is dark energy? The universe is expanding. This we've known for nearly a century, ever since Edwin Hubble noticed that distant galaxies are racing away from us, their light stretched out like echoes fading into space. But in 1998, something even stranger came to light. That expansion, rather than slowing down due to gravity, was speeding up. The universe wasn't just coasting outward, it was accelerating. Some invisible and mysterious force was pushing it apart faster and faster. Scientists gave it a name, dark energy, but the name is only a placeholder. In truth, we don't know what dark energy is, not even a little. Dark energy makes up nearly 68% of the total energy content of the cosmos. It is the dominant ingredient in the recipe of reality. More pervasive than stars or galaxies, more influential than gravity or light, it shapes the entire fate of the universe. And yet, it has never been seen, touched, or directly measured. It doesn't emit light, interact with matter, or leave fingerprints on particles. We know of its existence only through its effects. Its strange and persistent tendency to accelerate the stretching of space. It's as if the very fabric of the cosmos has developed a mind of its own, pushing outward with relentless force. To understand just how strange this is, imagine the universe as a vast balloon with galaxies painted on its surface. As the balloon inflates, the galaxies move away from each other, not because they're flying through space, but because space itself is growing. That's what cosmic expansion means. Now imagine that not only is the balloon expanding, but the rate of that expansion is increasing over time. That's the signature of dark energy. Something is inflating the universe faster than gravity can pull it back. It's as if space wants to run away from itself. But what exactly is this something? There are several possibilities, and each opens doors to even deeper mysteries. One idea is that dark energy is a property of space itself. This concept dates back to Albert Einstein, who introduced what he called the cosmological constant, a mathematical term he added to his equations to allow for a static universe. He later called it his biggest blunder when it became clear the universe was expanding. But now, with the discovery of acceleration, the cosmological constant is back in fashion. Perhaps empty space has a fixed amount of energy per unit volume, a gentle pressure that never fades, no matter how much space there is. If this is true, then the more space expands, the more dark energy there is. Not because the energy grows stronger, but because there's more space for it to inhabit. It's like a fog that doesn't thin out as the room grows larger. This simple model explains the data well, but it raises a question that borders on philosophical. Why does empty space have energy at all? And why does it have this specific amount? Quantum field theory suggests that space should have an enormous amount of vacuum energy, something like 10,120 times more than what we observe. This is known as the cosmological constant problem, and it's arguably the worst prediction in the history of physics. Other models treat dark energy not as a constant, but as something dynamic. A field, perhaps, that changes over time, what scientists call quintessence. In these models, dark energy evolves slowly, responding to the growth of the universe in ways we don't yet understand. It could grow stronger, fade away, or even reverse. If it does reverse, it might someday pull the universe back in on itself. If it grows stronger, it might tear the universe apart in a final big rip. Tom Abraham gives a Tony in the universe apart in a final big rip. These models allow for a more flexible future, but they also introduce new unknowns. What is this field made of? What rules does it follow? What set it in motion? There are even more exotic theories. Some propose that our understanding of gravity is incomplete, that what we interpret as dark energy is really a sign that gravity behaves differently on cosmic scales. These modified gravity theories rewrite the rules of general relativity, allowing for accelerated expansion without invoking an unknown force. Others look to extra dimensions, suggesting that dark energy is a spillover effect from a higher dimensional space beyond our perception. Still others imagine that our universe is just one bubble in a multiverse, and that the value of dark energy is a random variable that happens to allow galaxies, and therefore life, to exist in our particular bubble. Despite decades of effort, no single theory has won out. Observations are improving. Telescopes and space probes scan the sky, mapping supernovae, galaxies, and cosmic structures to trace the universe's expansion history. Projects like the Dark Energy Survey and the Euclid mission are designed to gather more data, to narrow down the possibilities. But every new data set only seems to confirm the same eerie truth. Something is pushing the universe apart, and we do not know what it is. Yet we do know this: it is not new. Dark energy has been part of the universe for a very long time. In fact, it likely began to dominate the cosmic story around 5 billion years ago, when its repulsive force overtook gravity's grip on large-scale structure. Before that, gravity slowed the expansion, but once the balance tipped, dark energy took over, and ever since, the universe has been accelerating outward, with galaxies drifting farther apart like embers scattered in the wind. If this continues, the future of the cosmos is a lonely one. Stars will fade. Galaxies will slip beyond view. The night sky will grow empty. Dark energy is not just a scientific puzzle, it is a philosophical one. It asks us to confront the limits of knowledge. How can the thing that defines the universe be so utterly beyond our grasp? How can something be so real, yet so hidden? It challenges our assumptions about matter, space, and the very structure of reality. It reminds us that our picture of the cosmos, no matter how refined, is still incomplete. There are forces at work that we cannot see, shaping destinies we cannot predict. And yet, there is something beautiful in this mystery. The fact that we can even ask these questions, that we have the tools, the curiosity, the language to explore the invisible, is extraordinary. Our minds, born from stardust, dare to understand the forces that govern the stars. We don't know what dark energy is, but we know it matters. We know it connects every galaxy, every corner of space, every future moment that has yet to unfold. Perhaps one day a new theory will emerge, a deeper equation, a sudden insight. Perhaps we will find that dark energy is not so dark after all, that it is the echo of a deeper harmony, a rhythm woven into the universe's silent song. Or perhaps it will remain forever beyond us, like the horizon of a dream we can never reach. Either way, we will keep searching, because to wonder is to be alive, and in wondering, we become part of the very mystery we seek to understand. Why is there far more matter than antimatter? Every moment, every movement, every breath you take relies on a quiet and profound cosmic imbalance. The atoms that form your body, the air you inhale, the stars in the sky, and the galaxies that dance across the night, all of them exist because of a tiny, mysterious asymmetry woven into the fabric of creation. According to the best understanding in physics, the Big Bang should have created equal amounts of matter and antimatter, but if that had happened, all those particles would have instantly collided with their opposites, annihilated in perfect balance, and left behind a universe filled with nothing but light. Instead, something strange occurred. Matter won, antimatter lost. And here we are. At first glance, the laws of physics appear to treat matter and antimatter as equals. For every type of matter particle, such as electrons or quarks, there is an antimatter counterpart with the same mass but opposite charge. When the two meet, they annihilate, releasing energy. In the early universe, with temperatures unimaginably high and particles flying in every direction, matter and antimatter should have been produced in perfect pairs. But if they were truly equal, they should have destroyed each other completely. There should be no stars, no planets, no people, just an empty sea of radiation. Yet the universe clearly contains matter. We see no large regions dominated by antimatter. We do not observe the telltale gamma rays that would be produced if matter and antimatter were still annihilating today on cosmic scales. Everything we can touch, measure, or observe appears to be made of ordinary matter. The antimatter is gone, and the lingering question is why? Physicists call this mystery the baryon asymmetry problem. Baryons are the family of particles that includes protons and neutrons, the building blocks of atoms. The asymmetry is the tiny but vital difference in the amount of matter versus antimatter that existed in the early universe. Estimates suggest that for every billion pairs of matter and antimatter particles, there was just one extra particle of matter. That 1 in a billion excess, after all the mutual annihilation, was enough to build everything in the universe, every galaxy, every star, every cell in your body. But where did that imbalance come from? What allowed matter to edge out antimatter by the slimmest of margins? The search for answers begins in the deep laws of physics. In 1967, Russian physicist Andrei Sakharov proposed 3 necessary conditions for the universe to develop a matter-antimatter imbalance. First, there must be interactions that violate the conservation of baryon number. The total number of matter particles must be allowed to change. Second, the laws of physics must violate charge parity symmetry, or CP symmetry, meaning they must treat matter and antimatter slightly differently. Third, the universe must have gone through periods of thermal non-equilibrium, where particles interact in a way that breaks time reversal symmetry. These 3 ingredients, baryon number violation, CP violation, and non-equilibrium conditions, are essential. But even with them, the known physics doesn't produce enough asymmetry to explain the observed universe. CP violation does occur in nature. We've seen it in certain decays of particles, called kaons, and B mesons. But the amount is minuscule, far too small to account for the matter-dominated cosmos we live in. It's as if the cosmic dice are weighted, but not nearly enough to produce the outcome we see. So physicists have gone searching for new sources of asymmetry. One idea is that there are unknown particles or interactions that exist only at high energies, energies that filled the universe in its first moments. These might be hinted at by extensions of the standard model of particle physics, such as supersymmetry or grand unified theories. These models introduce heavy particles that could decay in ways that favor matter over antimatter. If such particles existed in the early universe, their decays could have tipped the cosmic scales. Another approach involves leptogenesis, a theory that suggests the imbalance began not with baryons, but with leptons, a category that includes electrons and neutrinos. In this model, the decay of heavy neutrinos in the early universe could have produced more leptons than antileptons. Later, through a process known as Sphaleron conversion, some of that lepton asymmetry is transformed into baryon asymmetry. This elegant framework not only offers a path to matter dominance, but also connects with another mystery: the tiny but non-zero mass of neutrinos. If confirmed, it would offer a profound link between the smallest particles and the largest cosmic structure. Still, despite the beauty of these theories, none have yet been confirmed by experiment. The Large Hadron Collider and other particle accelerators have searched for hints of new particles and new CP-violating processes. So far, nature has been silent. The symmetry remains broken, but the mechanism is hidden, and the deeper we go, the more we realize how delicate and improbable our very existence is. If the asymmetry had been slightly different, if matter and antimatter had canceled more completely or less, our universe would look nothing like it does today. It might not exist at all. Some scientists have explored even stranger ideas. Perhaps our universe is not alone. Perhaps in the vast multiverse, there are other realms where antimatter won the battle, and those universes are filled with antimatter stars and antimatter life. Or perhaps there is a symmetry we haven't yet uncovered, one that exists on scales or dimensions we can't perceive. Some theories suggest mirror matter or hidden sectors, where balance is restored in ways invisible to us. These ideas remain speculative, but they speak to the profound strangeness of the puzzle. There is also the possibility that the imbalance is not fundamental at all, but an illusion born from an early quantum fluctuation, an accident of the universe's birth. But this too feels unsatisfying. Why should the laws of nature allow such a crucial imbalance to arise without a cause? Why would the very fabric of reality tip the scales so precisely, leaving just enough matter to form stars, worlds, and minds? The question presses against the boundaries of both science and philosophy. Yet despite the mystery, there is something awe-inspiring in the asymmetry. From a slight imperfection, a universe bloomed. From a 1 in a cillion sliver of imbalance, everything emerged: galaxies, oceans, forests, thoughts. The matter that forms your hands, your brain, your heart, all of it exists because of this cosmic anomaly. You are the residue of annihilation, a survivor of symmetry's collapse, a child of imbalance. And so the search continues. New experiments, more sensitive than ever before, are probing the behaviors of neutrinos, seeking new CP-violating effects. Underground detectors listen for rare decays that could signal the breakdown of baryon number conservation. Space telescopes map the cosmic microwave background with increasing precision, hunting for the faint fingerprints of the early universe's thermal history. Each observation is a step closer to the truth or a deeper mystery. The imbalance between matter and antimatter is not just a scientific problem. It is a story written into the very structure of the universe, one that touches on chance, on fate, and on the nature of reality itself. We do not yet know why matter prevailed, but the fact that we can ask, that we are here to wonder, is itself part of the answer. Perhaps in seeking the reason for this imbalance, we are really searching for the reason we exist at all. Do parallel universes or a multiverse exist? When you look up at the night sky, it's easy to imagine that the universe is all there is, a vast but singular expanse of stars, galaxies, and cosmic dust, unfolding through time and space. But some of the most daring ideas in modern science suggest something far more astonishing, that what we call the universe may be just a single bubble in a much larger reality. That beyond the cosmic horizon lies a deeper structure, the multiverse, a realm of countless other universes, each with its own laws, dimensions, and histories. Some may be like ours, others may be utterly alien. And yet, despite the grandeur of this idea, we have no evidence for it, nor any certainty that we ever will. The concept of a multiverse is not one theory, but many. It appears in various forms across cosmology, quantum mechanics, string theory, and even philosophy. Each version arises from different assumptions and frameworks, and each offers a unique vision of reality. One of the most accessible forms of the multiverse arises from cosmic inflation, the rapid expansion of space that is believed to have occurred in the first moments after the Big Bang. In many models of inflation, space doesn't stop inflating everywhere at once. Instead, it continues expanding eternally in some regions, while in others, it settles into bubble-like universes. Our universe may be one such bubble, floating in a vast foam of others, each birthed by their own localized Big Bangs. These bubble universes could have different physical constants, different particles, even different numbers of dimensions. In some, gravity may be stronger, stars might burn faster, or chemistry might never support life. If this inflationary multiverse is real, then we inhabit just one island in a boundless sea of possibilities. But even if this is true, how would we ever know? The space between these bubbles expands faster than light, placing them forever beyond our reach. We can't travel to them, see them, or communicate across the divide. They exist, if at all, on the outer edge of the imaginable. Another path to the multiverse emerges from quantum mechanics. According to the many worlds interpretation, every quantum event, every flip of a subatomic coin, causes the universe to split. In one branch, a particle goes left. In another, it goes right. In one universe, you turn left at the crossroads. In another, you go right. All possibilities exist, all at once, in a constantly branching tree of realities. This isn't just a philosophical idea. It's a mathematically consistent way of interpreting quantum theory without invoking wave function collapse. But it comes at a steep price, accepting that every possible outcome of every event does, in some sense, actually happen, in a version of reality you can never access. This idea is profoundly unsettling. It means that in some universe, every choice you didn't make was made. There's a version of you who took a different job, married someone else, lived a completely different life. Somewhere, perhaps, there's a version of you who never existed at all. These parallel lives are not fantasies, they are, according to the theory, just as real as your own. But they are sealed off, unreachable, flickering just beyond the veil of your present awareness. String theory, a proposed theory of everything, brings yet another version of the multiverse. In its equations, the universe requires more dimensions than we can see, 10 or even 11. These extra dimensions might be curled up in tiny shapes called Calabi-Yau manifolds. But there are many ways to compactify these extra dimensions, leading to an enormous landscape of possible universes, each corresponding to a different vacuum state of string theory. This landscape may contain as many as 10 to the power of 500 different possible worlds. Our universe is just one. Why this one? Why these laws, this physics, this balance of forces that allows stars to shine and life to evolve? In a multiverse, the answer may be simple. We live in a universe that permits life, because only such universes can be observed. This is known as the anthropic principle. It doesn't explain why the multiverse exists, but it does explain why we find ourselves in a universe finely tuned for life. In this view, our universe is not special because it was designed, it's special because we are here to see it. All other universes exist too, but they are lifeless, silent, unknown. This line of reasoning is controversial. Many physicists find it unsatisfying. It replaces prediction with selection. It blurs the line between science and philosophy. But it remains one of the few plausible answers to the question of cosmic fine-tuning. Some thinkers have even speculated about simulation-based multiverses. Perhaps our universe is not fundamental, but simulated by an advanced intelligence within a higher-level reality. In this scenario, countless simulated universes could exist, each with different initial conditions or laws. We might be characters in a vast computational experiment, unaware of the larger world beyond. While this idea borders on science fiction, it has been seriously considered by philosophers and physicists alike. But like other multiverse theories, it raises a troubling problem. If we're in a simulation, how would we know? What all versions of the multiverse share is a central challenge: testability. Science depends on observation, on falsifiability, on evidence, but other universes, by definition, lie beyond our cosmic horizon. If they exist, they may be forever cut off from us. We cannot touch them, visit them, or observe them directly, and yet their fingerprints might still be faintly detectable. Some models suggest that if another universe collided with ours in the early cosmos, it could leave imprints in the cosmic microwave background, subtle anomalies in the radiation that fills space. So far, such signals remain speculative, but new data may sharpen our search. Despite the lack of evidence, the multiverse remains compelling because it emerges naturally from theories we already trust. Inflation, quantum mechanics, and string theory, none of these were invented to create multiple universes. But in pushing their equations to the limit, they lead us there anyway. The multiverse may not be a choice, but a consequence. If so, we must grapple with a new picture of reality, one that is vastly larger and more varied than anything we once imagined. But there is another side to this story. For all its appeal, the multiverse raises philosophical and existential questions. If everything that can happen does happen somewhere, what does that say about meaning, about morality, about responsibility? Are we just one thread in an infinite tapestry, no more significant than any other? Or does our awareness, our choices, our love and longing still matter, even in an infinite sea of worlds? Perhaps the multiverse is not meant to make us feel small, but connected. That we are part of a deeper pattern, a vast unfolding of possibilities. That existence is richer, stranger, and more beautiful than we ever dared believe. Or perhaps the multiverse is a mirror, not of the cosmos, but of the human mind. Our need to explore, to question, to reach beyond, to ask what lies beyond the edge of what we know. So, do parallel universes exist? We don't know. We may never know. But the question remains open, alive, full of wonder. It challenges our assumptions, stretches our imagination, and reminds us that even in the age of satellites and quantum computers, mystery still reigns. We are not done discovering, not even close. The universe, or the multiverse, has more to say, and we are here to listen. What is inside a black hole? Black holes are among the most mysterious and terrifying objects in the universe, not because of what we see, but because of what we cannot. These cosmic abysses pull everything into their depths with such overwhelming gravity that not even light can escape. We can observe their effects from afar, watching stars spiral around invisible points, feeling the tremor of their collisions ripple through space-time. But once something crosses the boundary known as the event horizon, it is gone from view forever. No signal, no echo, no information returns. What lies inside a black hole is hidden from the universe, locked behind a veil of darkness. And yet, the mystery is deeper still, because even our best theories, relativity, quantum mechanics, fail us when we try to describe what happens within. The event horizon is the defining feature of a black hole. It's not a surface or a wall, it's a boundary in space-time. Once an object crosses it, it cannot come back. From the outside, anything falling in appears to slow down and freeze, never quite passing through. But from the object's own point of view, it plunges in freely, unimpeded, toward a central point of infinite density, the singularity. It's at this singularity where our understanding of physics breaks down completely. According to Einstein's general theory of relativity, the mass of the black hole is compressed into a point of zero volume and infinite density, a place where space and time themselves are twisted beyond recognition. But infinities in physics are usually signs that something's gone wrong, that our equations are being pushed beyond their limits. This is where the conflict between general relativity and quantum mechanics becomes sharp. General relativity describes gravity on cosmic scales, planets, stars, galaxies, and it tells us that mass warps space and time. But quantum mechanics rules the microscopic world, particles, atoms, and the vacuum itself. Each theory works beautifully in its own realm. But they cannot both be true in the heart of a black hole, because inside the singularity, matter is crushed to the smallest scales imaginable, and gravity becomes infinitely strong. To understand what happens there, we need a theory that unites the two, a theory of quantum gravity. And that is something we don't yet have. What we do know is that black holes are not just simple objects that swallow things and grow. They seem to have structure, thermodynamics, and even entropy. In the 1970s, physicist Jacob Bekenstein proposed that black holes have entropy, a measure of disorder or information content. Stephen Hawking took this further and showed that black holes are not truly black. They emit radiation due to quantum effects near the event horizon. This Hawking radiation implies that black holes can slowly evaporate over time. But this leads to a new paradox. If black holes evaporate, what happens to the information about the things they swallowed? In quantum mechanics, information cannot be destroyed. But if a black hole disappears and leaves no trace, then that principle is violated. This is the black hole information paradox, and it remains unresolved. Some theories suggest that information is preserved in subtle patterns within Hawking radiation. Others propose that the event horizon stores this information like a hologram, a compressed record of everything that fell in. Still others entertain more radical ideas, that space-time itself is emergent, that the fabric of the universe is built from entangled bits of quantum information. In these views, black holes become testing grounds for the deepest questions about reality. They are not just holes in space, they are windows into the edge of what is knowable. Some models suggest that what lies at the core of a black hole is not a singularity, but something else. A new kind of structure, perhaps stabilized by quantum gravity. Loop quantum gravity, a theory that attempts to quantize spacetime, proposes that the singularity is replaced by a region where quantum effects prevent total collapse. Instead of a point of infinite density, there may be a finite but exotic state of matter, something we do not yet have the tools to describe. In string theory, another candidate for quantum gravity, the singularity might be replaced by strings or brains vibrating at the Planck scale. Some ideas even suggest that the interior of a black hole connects to another universe, a wormhole, or Einstein-Rosen bridge. But these are still theoretical sketches, not settled truths. There's also the proposal that a black hole interior is a kind of holographic projection. According to the holographic principle, all the information inside a volume of space can be encoded on its boundary. If this idea holds, then the inside of a black hole might not need to exist in the usual sense. It may be fully described by what happens at the event horizon. From the outside, this boundary contains all the clues. From the inside, space-time may unfold according to entirely different rules. It challenges our notions of locality and reality itself. But no one has ever seen inside a black hole. No probe has returned from beyond the event horizon. No image has ever revealed its secret heart, and perhaps none ever will. The singularity, or whatever replaces it, remains hidden behind a curtain that no light can pass through. Even the Event Horizon Telescope, which famously captured the silhouette of a black hole's shadow, shows only the region just outside. The inside remains untouched, untouchable. Yet in our minds, we travel there again and again, trying to make sense of the place where physics breaks. Black holes also force us to confront the limits of space and time. Inside the event horizon, time and space swap roles. The singularity lies not in the center of a static sphere, but in the future. Once you cross the horizon, you are drawn inward, not like falling toward a place, but like being carried toward tomorrow. You cannot stop. You cannot turn around. It is not a matter of falling, it is a matter of destiny. You move forward in time toward the singularity as inexorably as we all move toward the ends of our own lives. In that way, the interior of a black hole is not just a physical location, it is a metaphor. And maybe that's what makes black holes so compelling. They are cosmic paradoxes, places where our understanding fails, and yet, through that failure, we glimpse something deeper. They remind us that knowledge has edges, and that the most interesting truths lie just beyond them. They are the universe's most elegant questions, disguised as answers we cannot read. Inside a black hole may be a singularity, or a bounce, or a bridge, or nothing at all. Until we have a theory of quantum gravity, we are left with silence. But it is not an empty silence. It is the silence of possibility, of the unknown waiting to be understood, of nature whispering truths that we have not yet learned how to hear. And so we keep listening, we keep asking. Because the mystery inside a black hole is also the mystery inside ourselves. What lies at the center of all things? What happens when we reach the edge? And how much more is there inside the dark? What is the true nature of quantum reality? Beneath the surface of everything we see and touch, reality behaves in ways that seem to defy logic, intuition, and even common sense. This is the world of quantum physics, a world where particles are not just possibility, where something can be here and not here at the same time, where the very act of looking changes what is being looked at. It is a reality stranger than science fiction, and yet it forms the foundation of all matter, energy, and interaction. And at the heart of this strange world lies an even deeper puzzle. What exactly is happening when we observe a quantum system? What does it mean when a particle that could be in many places suddenly appears in just one. What is the true nature of quantum reality? To understand this mystery, we have to begin with the basics. In the quantum world, particles like electrons or photons are described not as having definite positions or paths, but as existing in a superposition of all possible states. This is not just uncertainty, it's a genuine blend of realities. An electron might be spinning clockwise and counterclockwise at the same time. A photon might take every path through a maze of mirrors simultaneously. This idea is mathematically expressed by a wave function, a formula that contains all the probabilities of where the particle might be found or what state it might be in. But here is where things become truly strange. As long as no measurement is made, the wave function evolves smoothly and deterministically according to the Schrödinger equation. It's like a graceful dance of possibilities. But the moment we observe or measure the system, that elegant superposition seems to collapse into a single outcome. The electron is found spinning one way, not both. The photon appears on one path, not many. The wave function full of potential vanishes, and one concrete result remains. Why does this happen? What causes the collapse? And what does it mean about the nature of reality? This is known as the measurement problem, and it is one of the deepest unsolved puzzles in all of physics. The math of quantum mechanics works beautifully. It predicts the behavior of particles with astounding precision. It has given us lasers, semiconductors, MRI machines, and atomic clocks. But it doesn't tell us why one outcome happens when we look. It doesn't tell us what's really going on when possibility becomes fact. And because of this, quantum physics isn't just a theory about particles. It's a theory about knowledge, about observation, about consciousness. It blurs the boundary between what exists and what is seen. One interpretation of quantum mechanics, the Copenhagen interpretation, favored by Niels Bohr and others, says that quantum properties don't exist until they are measured. The act of observation brings the outcome into being. Before you look, the particle has no definite position. After you look, it does. But this raises a troubling question. What counts as a measurement? Is it a machine, a human mind, a camera? If observation creates reality, then whose observation? And what was the universe doing before anyone was around to observe it? Other interpretations try to sidestep this problem. The many worlds interpretation, proposed by Hugh Everett in the 1950s, says that all possible outcomes actually happen, but in different branching universes. When you measure a quantum system, the universe splits. In one branch, the particle goes left, in another, it goes right. You only experience one outcome, but the others are just as real in other versions of reality. In this view, the wave function never collapses. It just evolves into a vast branching tree of worlds, each containing a different version of events. It's a bold and elegant solution, but it comes with a cost. Accepting that the universe is constantly splitting into an infinite number of unseen realities. Then there is the pilot wave theory, also known as Bohmian mechanics. It proposes that particles do have definite positions at all times, guided by a hidden wave, a pilot wave, that determines their motion. The wave function is still there, but it doesn't collapse. It simply directs the particle along a particular path. This interpretation restores a kind of realism to quantum physics. Particles exist whether we look or not, but the price is non-locality, meaning that what happens in one place can instantly affect what happens elsewhere, even across vast distances. This seems to violate our intuitive ideas of causality, yet it is consistent with experimental results. Another line of thinking centers on decoherence. In this view, the environment plays a crucial role. When a quantum system interacts with the surrounding world, air molecules, light, heat, it becomes entangled with it, and its wave function appears to collapse. But technically, no collapse has occurred. Instead, the system's superpositions become so entangled with the environment that they can no longer interfere with each other. The result is that we see only one outcome, because the others are hidden in vast, inaccessible combinations of quantum states. Decoherence explains why quantum weirdness disappears in the macroscopic world. But it doesn't solve the measurement problem, it just explains why the outcomes seem classical. And then there is the most provocative idea of all, that consciousness itself plays a role. Some interpretations suggest that it is the awareness of the observer, the presence of a conscious mind, that causes the collapse of the wave function. This is a controversial and highly debated idea, but it raises profound questions. If consciousness affects quantum systems, then consciousness is not just a passive observer of reality, it is an active participant. It means that the mind is woven into the fabric of the cosmos in a fundamental way, that awareness might be a bridge between the possible and the actual. But many physicists reject this idea, preferring to keep consciousness separate from physical theory. They argue that we don't need minds to explain measurements, just better physics. Still, the question lingers. Because at the heart of quantum mechanics lies something deeply unsettling, the line between observer and observed is not so clear. In trying to measure the universe, we become part of the experiment. In trying to understand the wave function, we find ourselves inside it. Some philosophers suggest that quantum mechanics reveals something profound about the nature of information itself, that reality is not made of things, but of relationships, interactions, correlations, probabilities. In this view, particles don't have properties independently. They only have properties when related to something else. Reality is not a set of objects, but a web of entanglements. The universe is not a machine, but a process, a constant unfolding of potential into experience. And yet, the mystery remains. What is the true nature of quantum reality? Is the wave function real, or just a mathematical tool? Does the universe split at every decision, or does it follow a single hidden path? Are particles truly uncertain, or just unknowable? Are we creating reality as we observe it, or discovering something that was already there? The answers are not yet known, and perhaps, in some sense, they never will be. But there is something beautiful in this not knowing. Quantum mechanics does not just challenge our physics, it challenges our philosophy. It asks us to rethink what it means to be, to know, to see. It reminds us that the universe is not a clockwork machine, ticking predictably into the future, but a shimmering field of possibility, shaped by chance and choice and perspective. It teaches us humility, that beneath the surface of certainty lies a deeper realm, where mystery is not an obstacle, but a truth. And so we keep asking. We build new experiments, we tangle photons, trap atoms, push the boundaries of precision. We try to catch the moment when a quantum possibility becomes a concrete reality. But the answer stays just out of reach, like a shadow in the fog. What is real, what is observed, and what is merely imagined? These are not just questions of physics. They are questions of being, of meaning, of what it means to live in a world where even the smallest things refuse to be pinned down. Why are the laws and constants of nature set the way they are? The universe appears to be a place of remarkable precision. From the rhythm of planetary orbits to the balance of nuclear forces inside atoms, everything seems to unfold according to invisible rules. Rules that are elegant, consistent, and above all, incredibly specific. These rules are encoded in the laws of physics, and woven into those laws are a handful of numbers known as the fundamental constant. These include the speed of light, the gravitational constant, Planck's constant, the charge of the electron, and many others. Together, they define how the universe behaves. And what's truly astonishing is how precisely they must be tuned for the universe as we know it to exist. If any one of these constants were even slightly different, the consequences would be dramatic. If gravity were just a bit stronger, stars might burn too quickly and collapse before life could evolve. If it were weaker, stars might never form at all. If the charge of the electron were off by a tiny fraction, atoms would not be stable. If the strength of the strong nuclear force were altered even slightly, the chemistry required for life might never emerge. These constants are not just numbers, they are the pillars of existence. And yet, we have no idea why they are set the way they are. Why these values? Why this balance? Why this universe? This question, why the laws of nature are what they are, sits at the very edge of human understanding. It's not just a matter of measurement or calculation, it is a philosophical and existential riddle. We can measure these constants with exquisite precision. We can write them into equations, test their implications, and build technologies based on them, but nowhere in the equations does it say why the values are what they are. The laws work, but the origin of their parameters remains hidden. Some physicists have hoped that a theory of everything might one day reveal the deeper reason. Perhaps a more fundamental framework, such as string theory, or some yet unknown unifying principle, will show that the constants we observe are not arbitrary, but inevitable, that they arise from deeper symmetries, or from the shape of some higher dimensional geometry. This is a beautiful idea, but so far no such theory has emerged, and some versions of string theory seem to suggest the opposite, that there are many possible universes, each with different constants. In that view, what we call fundamental is not fundamental at all. It's just local. This brings us to one of the most controversial and intriguing explanations, the anthropic principle. It states that the constants are what they are because if they were different, we wouldn't be here to observe them. In other words, our universe is one among many, perhaps in a multiverse, and we happen to live in a universe whose constants support life. There's no deeper reason. It's selection bias. We see a universe that supports life because only such universes can be seen. This idea has a certain logic, but it feels unsatisfying to many. It doesn't explain why the multiverse exists. It replaces a mystery with a statistical shrug. And yet, it might be the best answer we have. Others believe that the constants might not be constant at all. Some speculative theories propose that over cosmic timescales, the values of fundamental constants could evolve. If true, that would revolutionize our understanding of physics. But the evidence so far suggests remarkable stability. The speed of light, the strength of gravity, the ratio of forces, these numbers appear to be fixed, at least within the limits of current observation. The universe, it seems, has chosen its numbers carefully, but we don't know why. And then there's the possibility that there simply is no reason, that the values are random, set at the birth of the universe like the roll of cosmic dice. This is deeply unsettling. It means the structure of reality is founded on chance, that the laws we consider universal are not necessary but contingent. In a different role, the universe might have been sterile, chaotic, or stillborn, or there might be no universe at all. If this is true, then our existence rests on a knife's edge of probability, an improbable miracle surrounded by a sea of unobservable might-have-beens. But not everyone is willing to accept this. Some thinkers propose that the laws of nature must be what they are, that there is only one logically consistent way for a universe to exist, that the constants we see are not chosen but required. This view echoes the mathematical Platonism of thinkers like Max Tegmark, who suggest that the universe is not just described by mathematics, it is math. In this view, reality is the unfolding of a single inevitable equation. But if that's the case, then why does that equation permit beauty, complexity, and consciousness? And that raises another layer of the mystery, not just why the universe exists or why it has laws, but why those laws give rise to life, to awareness, to beings who ask questions about the laws. The constants are not just tuned for chemistry or gravity, they seem tuned for thought, for reflection, for wonder. Is this coincidence? Is it a hint? Or is it merely the echo of our own existence, bouncing back at us from the silence? Some turn to spiritual or metaphysical answers. They see in the fine-tuning of the universe a kind of intention, a design, not necessarily the hand of a deity in the traditional sense, but a guiding principle, a source, a deeper order. Others see the same facts and find the opposite, proof that there is no plan, only chance, that the universe is a vast, indifferent mechanism and we are temporary accidents within it. The data is the same, the interpretation changes. Because at the root of this mystery lies not just physics, but philosophy. And yet, the mystery endures. We build particle colliders, peer into deep space, write equations on blackboards. We measure the constants to more and more decimal places. But the why remains. The universe is full of patterns, but the origin of the pattern is veiled. We are like children who have found a clock, ticking with perfect precision, but no one can say who wound it or if it wound itself. The more we learn, the more we realize how much we do not understand. But perhaps the beauty lies not in the answer, but in the question. That we live in a universe where the laws are knowable at all is itself a wonder. That there are constants, that they can be measured, that they give rise to structure and meaning, that is something extraordinary. In a world that could have been chaos, we find symmetry. In a cosmos that could have been empty, we find form. And in the silence of the laws, we find the music of existence. So why are the constants what they are? We don't know, not yet. Perhaps we never will. But the search continues, because to ask this question is to reach beyond, to touch the edges of what is known and peer into the possible. It is to stand at the shore of the infinite and wonder what lies beyond the horizon. And in that act of wondering, we become part of the story the constants tell. Not just observers of the universe, but participants in its unfolding mystery. How did life originate from non-living matter? There is a moment hidden deep in the past, so quiet and subtle that it leaves no clear trace, and yet it changed everything. It is the moment when life began, when a world of lifeless chemicals stirred, organized, and took a breath of something more. Before this moment, the earth was just a ball of rock and water, storms and sunlight, a planet among planets. Afterward, it became a cradle of living complexity. From that first spark, a continuous thread leads to every tree, every bird, every person. And yet, despite all our science, we still do not know how it happened. How did life arise from non-life? How did matter learn to replicate, to evolve, to feel? This question, the origin of life, is one of the greatest unsolved puzzles in all of biology. It sits at the intersection of chemistry, physics, and chance. We know that the Earth formed about 4.5 billion years ago, and we have evidence that life began relatively soon after, by about 3.8 billion years ago. Simple celled organisms were already thriving in the oceans. That leaves a window of just a few 100 million years for life to emerge from inanimate matter. But how? The first step is understanding what we mean by life. Living systems have certain core properties. They replicate, they evolve, they maintain internal environments, they respond to stimuli, and crucially, they process information encoded in molecules like DNA and RNA. So to create life from non-life, a set of molecules had to come together and begin doing these things. Somehow chemistry had to cross the line into biology. But where is that line, and how is it crossed? One of the oldest and most enduring ideas is the primordial soup theory. First proposed in the 1920s by Alexander Oparin and J.B.S. Haldane, it suggests that early Earth had a reducing atmosphere, rich in hydrogen, methane, ammonia, and water vapor. Lightning, ultraviolet radiation, and volcanic heat could have triggered chemical reactions, producing organic compounds like amino acids and nucleotides. These would accumulate in oceans and ponds, forming a nutrient-rich soup from which life could eventually emerge. In 1953, the famous Miller-Urey experiment gave this theory experimental support, showing that simple gases, sparked with electricity, could produce building blocks of life. But making molecules like amino acids is just the beginning. Life requires much more than that. Those molecules must be assembled into complex structures, proteins, membranes, genetic codes, and more mysteriously, must begin to organize themselves, to replicate, to evolve. One idea is that life began with metabolism. In this metabolism-first view, networks of chemical reactions became self-sustaining before genetic information emerged. Small molecules, catalyzed by minerals or metal ions, could form cycles, like the citric acid cycle we see in cells today. These cycles might have gradually built complexity, laying the groundwork for more structured forms of life. Another compelling theory is the RNA world hypothesis. It proposes that RNA, an information-carrying molecule similar to DNA, was the first molecule capable of both storing information and catalyzing chemical reactions. In this view, early Earth produced simple RNA strands, some of which could fold into shapes that allowed them to replicate themselves. Over time, these RNA molecules evolved greater complexity, eventually giving rise to DNA and proteins. This theory has strong support because RNA has been shown to act as both a gene and an enzyme. But creating RNA from scratch under prebiotic conditions has proven difficult in the lab. The chemistry is fragile, the steps are intricate, and so the question lingers: could it really happen naturally? Still, other theories focus on environments rich in energy and chemistry, like deep-sea hydrothermal vents. These underwater fissures release mineral-rich heated fluids from within the Earth's crust. Here, in darkness, life might have begun, fueled not by sunlight, but by chemical gradients. The unique structure of these vents, filled with microscopic pores and catalytic surfaces, could have served as natural incubators for primitive life. Molecules concentrated, reactions stabilized, and cycles emerged. In this environment, protected from the chaos of the surface, life might have taken root. And then there's the idea that life didn't start on Earth at all. The theory of panspermia suggests that life or its precursors arrived from space, perhaps carried on comets, asteroids, or interstellar dust. Some meteorites have been found to contain organic compounds, and we know that amino acids can form in space. If early Earth was seeded with these ingredients, they might have jump-started the origin of life. But even if panspermia is true, it simply pushes the question further back. How did life begin elsewhere? There are other proposals, each focusing on different pieces of the puzzle. Some scientists look at clay minerals, which can bind organic molecules and might have served as scaffolds for early chemistry. Others study lipid vesicles, tiny bubbles of fat-like molecules that can form spontaneously in water and resemble the membranes of modern cells. These vesicles might have trapped useful molecules, allowing early life to form compartments and organize reactions. Still, others investigate the role of ice, suggesting that freezing temperatures might have concentrated molecules and slowed degradation, helping life to begin in the cold. But so far, no single theory has explained everything. We have fragments, pieces of the story. We can create amino acids in the lab. We can form membrane-like vesicles. We can even build primitive RNA strands. But assembling all the parts into a system that replicates, evolves, and sustains itself, that remains out of reach. And so, the origin of life continues to be a great scientific mystery, suspended in a silence that science has not yet broken. Still, the mystery is not failure, it is possibility. Every unanswered question is an invitation. Every experiment brings us closer, and perhaps, in the process, we are learning something deeper, not just about life, but about complexity, emergence, and the nature of being. Life is not just molecules. It is a pattern, a dance, a self-sustaining flame that feeds on structure and flow. Understanding how it begins is not just about chemicals. It is about how order arises from chaos, how systems form from noise, how something new is born from the inanimate. And there is a quiet poetry in this search, that we, living beings made of cells and strands and thoughts, are trying to understand how the first spark began. We are life, studying life's beginning. A loop of awareness, reaching backward in time to understand what set it all in motion. Whether it was in a warm pool, a deep vent, a frozen lake, or a cloud of interstellar dust, life began once, and in that beginning lies the story of everything. What exactly makes humans unique? We walk among the animals, yet apart from them. We share their bodies, their instincts, even much of their DNA. Our hands resemble the paws and wings and claws of other creatures. Our brains are shaped by evolution, not design. And still, something changed. Somewhere along the path of time, a leap occurred, subtle at first, then profound. We began to ask questions. We began to make tools, not just use them. We told stories. We created art, wrote music, built civilizations. In a few thousand years, a blink in evolutionary time, we transformed the world. But how? What allowed us, among all the animals, to become what we now are? The question of what makes humans unique is one of the deepest and most elusive in all of science. At the genetic level, we are astonishingly similar to chimpanzees, sharing roughly 98.8% of our DNA. Even with mice, the overlap is around 85%. Biology reminds us that we are not separate from nature, but part of it. Yet something in us is undeniably different. We launched spacecraft to the moon. We mapped the human genome. We write poetry and perform surgery. No other species builds cities, crafts symphonies, or contemplates the origin of the cosmos. So, what changed? One answer points to our brains. Human brains are larger, relative to body size, than those of most animals. But size alone does not tell the whole story. Elephants and dolphins have large brains too. What seems more important is how our brains are structured, particularly the neocortex, the part involved in reasoning, planning, and language. Our brains are wired for abstraction, for simulation, for imagination. We can hold ideas in our minds that aren't tied to the present moment. We can imagine futures, remember distant pasts, and construct scenarios that never happened. This mental time travel lets us learn not just from experience, but from story. Language is another key. While many animals communicate, whales sing, bees dance, monkeys shout, human language is different. It is symbolic, recursive, infinite in its expressiveness. We can describe not just things, but ideas. We can share complex thoughts, ask questions, lie, joke, hypothesize. With language, we don't just communicate, we teach, organize, and preserve knowledge. Oral traditions became writing, writing became history, history became civilization. Language allowed minds to merge across generations, building a cumulative culture unlike anything in the animal kingdom. But even language may not be the full answer. After all, language must be learned, and it depends on something deeper: social cognition. Humans are uniquely skilled at what scientists call theory of mind, the ability to attribute thoughts, intentions, and feelings to others. We don't just see behavior, we infer mental states. This lets us cooperate, deceive, empathize, and build complex relationships. From early childhood, we navigate a world not just of objects, but of other minds. Our social intelligence is extraordinary. We form alliances, follow leaders, enforce norms. We shape and are shaped by each other's thoughts. This social mind underpins something else: culture. Culture is more than habits or traditions. It is shared knowledge, passed through learning, not genes. It is the invisible architecture of behavior, shaping everything from art to morality. Animals have culture in limited forms. Certain birds teach songs, some apes use tools. But only humans have cumulative culture. We build on the discoveries of those before us. Each generation inherits not just genes, but stories, skills, systems. This ratchet effect, where innovations are preserved and expanded, has no known parallel in the natural world. Another piece of the puzzle may lie in our hands. Human hands are extraordinarily dexterous. With opposable thumbs and fine motor control, we manipulate objects with precision. We shape tools, carve wood, weave cloth. Tool use is not unique to us. Many animals use tools, but our tools became technologies. A sharp rock became a knife. A spear became a missile. Fire became electricity. Our hands turned thought into form, idea into object, and over time these objects transformed our environment and ourselves. But tools alone don't build cathedrals. Something more abstract may set us apart: symbolic thought. Humans represent the world not just as it is, but as it could be. We create myths, rituals, religions. We paint on cave walls, bury our dead, wonder about gods. This symbolic imagination allows us to live in multiple realities: the physical and the conceptual, the actual and the dreamed. We give meaning to things. A piece of cloth becomes a flag. A sound becomes a prayer. A gesture becomes a promise. No other species lives so fully in the symbolic realm. and in that realm we find morality. Humans don't just act, we judge. We build systems of right and wrong, justice and duty. While other animals may show empathy or fairness in simple forms, human morality is complex, reflective, and communal. We create laws, debate ethics, sacrifice for ideals. Our sense of self extends beyond the individual to family, tribe, nation, species. We are not just intelligent, we are moral beings, capable of shame, compassion, and consciousness itself may be the deepest layer. All animals are conscious in some form. They feel, respond, navigate. But human consciousness is self-aware. We reflect on our thoughts, question our beliefs, imagine ourselves in others' shoes. We tell stories about who we are and seek meaning in what we do. We are aware that we are aware. And in that recursive loop, something profound arises: identity, purpose, wonder. Still, it's important to remember that human uniqueness is not absolute. It is not that we have traits no other animal possesses, but that we combine them in a particular way, to a particular degree. We are the result of countless tiny changes, evolutionary experiments shaped by time, chance, and necessity. Our uniqueness is not magic, it is emergent, complex behaviors arising from simple rules played out over millions of years. Some scientists argue that what truly sets us apart is not one trait but synergy, a convergence of language, tool use, sociality, and memory that created a tipping point. A threshold was crossed, and feedback loops took over. Culture fed technology, technology fed cooperation, cooperation fed knowledge, and knowledge fed the transformation of our world. We became a species that shapes its own evolution, not just biologically, but culturally and mentally. And yet, for all our uniqueness, we are still animals. We hunger, fear, sleep, reproduce. We are bound by instincts, by emotions, by mortality. We are made of cells and atoms, just like every other creature. What makes us human is not that we escape nature, but that we carry it with us and build upon it. We are nature becoming aware of itself, and that awareness carries responsibility. Perhaps the real question is not what makes us unique, but what do we do with that uniqueness? We can destroy or protect, exploit or nurture. We can create beauty or cruelty. We can reach for the stars or ruin our home. Our gifts are not guarantees. They are invitations. To be wise, to be kind, to be curious, to imagine. So, what makes us human? Maybe it's not just our brains, or our language, or our tools. Maybe it's our questions, our hunger to understand, our need to connect, our longing for meaning. The fact that we can ask what makes us different and care about the answer may be the most human thing of all. What is consciousness, and how does it arise? We awaken each day into a world we can see, feel, and think about. We remember our past, anticipate our future, and reflect on the present. We are not just passive observers, we are aware. We don't just respond to the world, we experience it. This simple truth is the most immediate thing we know. Before thought, before language, before science or story, there is consciousness, the feeling of being. And yet, for all its intimacy, the origin and nature of consciousness remain a mystery so profound that it lies at the very edge of science and philosophy. What is consciousness? How does it arise from the gray, silent machinery of the brain? Why does the firing of neurons give rise to the brightness of thought, sensation, and self? We know that consciousness exists. It is not a theory, it is the very ground of our being. Every experience, every feeling, every perception unfolds within it. But defining it is another matter. At its core, consciousness refers to subjective experience, what it's like to be, to feel pain or pleasure, to see red, to remember a song, to worry or to hope. Philosophers call this the hard problem of consciousness, not how the brain performs tasks or processes information, but why any of it feels like anything at all. Why is there an inner life? Why is the brain not just a computer, churning data without awareness? In neuroscience, much progress has been made in understanding the correlates of consciousness, the brain states that accompany awareness. We can scan the brain and see which regions light up when a person feels fear, sees an image, recalls a memory. We know that the cerebral cortex, particularly the prefrontal and parietal areas, plays a key role. We know that damage to certain areas can disrupt consciousness, and that anesthesia can turn it off like a light. But even as we map the brain in increasing detail, the core question remains untouched. How do these neural patterns create the vivid, first-person world we live in? How does matter become mind? One popular approach suggests that consciousness arises from complexity. The brain is not just active, it is deeply interconnected. Billions of neurons form intricate networks with constant feedback loops and layered processing. The Integrated Information Theory, or IIT, proposes that consciousness corresponds to the amount of integrated information a system can generate. According to IIT, consciousness arises when a system is both highly differentiated and unified, when it can hold many states, yet behave as a whole. But even if this is true, it doesn't explain why integration should produce experience. It offers a measure, but not a mechanism. It tells us when consciousness might appear, but not why it feels like anything. Another idea is global workspace theory. In this view, the brain contains many unconscious processes running in parallel: vision, hearing, memory, emotion. Consciousness emerges when information from these processes is broadcast to a central workspace, where it becomes globally available. What we experience as awareness is the content that wins the competition for attention and becomes part of this shared stage. Again, this explains aspects of how consciousness behaves, why it is limited, why it feels unified, but it doesn't penetrate the core mystery. Why should broadcasting information to a workspace feel like being? Some theorists suggest that consciousness may not arise from physical processes at all, but be a fundamental feature of reality. This is the view known as panpsychism. In this perspective, consciousness is not something that emerges at a certain level of complexity. It is built into the fabric of the universe. Just as mass and charge are basic properties of matter, so too is some form of experience. Atoms may not be conscious like humans, but they may possess proto-conscious qualities, which combine in more complex systems to form minds. This idea sounds radical, but it reflects an ancient intuition that mind and matter are not separate, but deeply intertwined. Others propose that consciousness is not a property of the brain alone, but of the relationship between the brain and the world. In this inactive view, consciousness is not something the brain has, but something it does. It is a dynamic process, arising through interaction. We are conscious not just because of what happens inside our heads, but because of the way we move, perceive, and respond. Consciousness, in this view, is not locked inside the skull. It is embodied, embedded, extended into the world. And then there is the role of attention. Some researchers believe that consciousness is closely tied to what we attend to. that awareness is the brain's spotlight selecting from the flood of information what enters our inner experience. But again, this raises a deeper question. Why is the spotlight illuminated at all? Why doesn't the brain just process information in the dark? Despite all the theories, the fundamental gap remains between neurons and qualia, between electrical signals and the feeling of sadness, between a brain and a mind. No one knows how to bridge it. Some even wonder if it can be bridged, if the subjective nature of consciousness makes it inherently beyond the reach of objective science. Others argue that this is a temporary impasse, that new paradigms will one day dissolve the mystery, just as the mysteries of life and the cosmos once seemed unknowable. But consciousness is not just a scientific problem, it is a philosophical and existential one. It touches on identity, free will, suffering, joy. It shapes our ethics, our spirituality, our understanding of what it means to be alive. Without consciousness, there is no world, no meaning, no self. It is the lens through which all else is seen, and so the mystery is not just that we are aware, but that we are aware of being aware, that we can reflect, doubt, create, that we can dream. Some suggest that consciousness is an illusion, that it is a narrative the brain tells itself, a user interface for complex computation. But if it is an illusion, it is the most convincing illusion in existence. An illusion that feels, loves, fears, hopes. Others seek the origin of consciousness in evolution, suggesting that it emerged as an adaptive trait, a way to model the environment, predict outcomes, and survive. But this too raises the question, why should evolution produce experience rather than just behavior? There is also the idea that consciousness is a threshold, a spectrum, not a switch, that simpler organisms possess simpler forms of awareness, that consciousness is not all or nothing but layered, like light through fog. If this is true, then perhaps the question is not how does consciousness arise, but how does it deepen? And still, we return to the silence. We can describe the brain in detail. We can measure waves, map networks, simulate perception, but the moment of awareness, the inner glow of being, remains untouched. It is the one thing we know directly, yet cannot explain. It is the presence behind every thought, yet absent from every equation. Perhaps the mystery of consciousness is not a problem to be solved, but a frontier to be explored. A mirror showing us who we are. Perhaps it is not about answers, but about insight. That in wondering, we become more conscious. That in the act of asking, we honor the very thing we seek to understand. So what is consciousness, and how does it arise? We do not know, but the search is sacred, because in it we are not just studying the mind, we are touching the essence of our own existence, and maybe, just maybe, that awareness is enough. A quiet light, flickering behind the eyes, asking not to be solved, but to be seen. Do we have free will, or is everything predetermined? You make a choice to speak, to turn, to pause, to think. And in that quiet moment, it feels like you are free, like the decision came from you and nowhere else, not from the past, not from some machine of cause and effect, but from within. This sense of agency, of authorship over your own life, is perhaps the most intimate feeling we know. Yet beneath that feeling lies a question as old as thought itself. Do we truly have free will? Or are all our choices determined by forces beyond us? Is our sense of freedom real, or just a story the brain tells itself? The debate between free will and determinism stretches across centuries, philosophies, and disciplines. In a deterministic universe, every event is the inevitable result of what came before. If you knew the position of every atom and every law that governs them, you could, in principle, predict every future event, every motion, every word, every heartbeat. This view, rooted in classical physics and championed by thinkers like Laplace, sees the universe as a clockwork machine, perfect, orderly, and inevitable. And if that's true, then where is the room for free will? Science reinforces this tension. Neuroscience has shown that many decisions begin in the brain before we become consciously aware of them. In experiments, researchers can sometimes predict what choice a person will make several seconds before the person reports making it. If the brain is already in motion before the you becomes aware of the choice, then is the conscious self really in control? Are we merely passengers, witnessing the unfolding of decisions already made? Genetics and psychology add more weight. We are shaped by our DNA, by our upbringing, by cultural norms, by past trauma, by biology we didn't choose. The desires that move us, the fears that restrain us, the values we uphold, these may all be inherited or conditioned. If your thoughts and behaviors are influenced by neurons and neurotransmitters, by hormones and histories, then where does freedom begin? And yet the feeling of choice is persistent. When you choose coffee over tea, when you speak or remain silent, when you act in defiance or in love, these do not feel like automatic outputs. They feel deliberated. They feel personal. Even if prior causes influence us, do they really determine us? That's where compatibilism enters the picture. Compatibilists argue that free will and determinism are not mutually exclusive. According to this view, we are free not because we are uncaused, but because we are caused in the right way. Our choices arise from our desires, beliefs, and reasoning. Those are shaped by the past, yes, but the process of making decisions still belongs to us. Think of a river carving its path through the land. The terrain shapes its course, but the water still flows. In this metaphor, determinism is the terrain, and free will is the current. Compatibilists believe that as long as our actions are not externally coerced, as long as they reflect our internal motivations, we are free, even if those motivations have a history. From this perspective, freedom is not the absence of causation, but the alignment between self and action. But others are not so convinced. Hard determinists argue that if everything is caused, then freedom is an illusion. You might feel like you could have acted otherwise, but you couldn't. Given the exact state of the universe at a moment in time, only one future is possible. The feeling of choice is just that, a feeling. A glitch in the system, like a dream of flight inside a cage. Then there are the libertarians, not the political kind, but the philosophical. They hold that true free will requires indeterminism, that at least some decisions must be free from causation. But here lies a paradox. If a choice is not determined by prior causes, does that make it random? If your decision is uncaused, how can it still be yours? How can freedom exist in the space between causality and chaos? Quantum mechanics has entered the conversation too. At the subatomic level, nature appears probabilistic. Particles do not follow deterministic paths, but rather unfold according to probabilities. Some have hoped this introduces space for free will, that perhaps the brain leverages quantum indeterminacy to escape determinism. But randomness is not freedom. If a decision is the result of a quantum fluctuation, it may be unpredictable, but is it truly chosen? Others look beyond mechanics to meaning. Perhaps free will is not about metaphysics, but about moral agency. In our social and ethical lives, we treat people as responsible beings. We praise, we blame, we punish, we forgive, all based on the idea that people could have acted differently. Our legal systems, our relationships, even our sense of self relies on the notion of accountability. If we reject free will entirely, what becomes of ethics? Can you be responsible for an act you were destined to perform? This is not just a theoretical problem. It touches on forgiveness and justice, on compassion and judgment. If someone's actions are the product of causes beyond their control, should we still punish them? Should we still hold them accountable? Or does understanding the web of cause and effect call for empathy rather than condemnation? Perhaps recognizing the role of circumstance can make us wiser, more patient, less harsh. And still, the mystery of the self remains. Who is the I that chooses? Is the self an agent or a narrative? Some neuroscientists suggest that the self is an emergent construct, a mental model the brain creates to track its own behavior. If so, then I is not a central command center, but a useful illusion, a story the brain tells about itself, useful for coordination, but not the ultimate author. Yet this illusion is powerful. It's the voice that says, I will. The whisper that says, I won't. Illusion or not, it shapes our lives. Perhaps the truth lies somewhere in between. Perhaps our choices are neither fully free nor fully fixed. Perhaps we are influenced by causes, but not enslaved by them. Perhaps freedom is not a state, but a skill, a practice, a kind of awareness. To pause, to reflect, to ask, why do I want this? Is this me or my fear? My history or my hope? In that moment of awareness, something shifts. We are no longer just reacting, we are responding. We are participating in the shaping of our path. And maybe that is what freedom really is. Not the absence of cause, but the presence of consciousness. Not the power to do anything, but the power to know why you do what you do. To act with intention. To recognize the forces within you and rise at times above them. The question of free will may never be settled in equations or experiments, but it may still matter deeply in how we live. Because whether or not we are free in the ultimate sense, we still must choose, we still must act, and in that choosing, we define ourselves not as independent of cause, but as the meeting place of thought and world, of past and possibility. Freedom may not be absolute, but it is enough to carry the weight of meaning, enough to strive, to hope, to change. So, do we have free will, or is everything predetermined? Perhaps both. Perhaps neither. Perhaps the answer is less important than the question, and the way we live in its shadow. Because in the asking, we awaken. In the asking, we become. Why do we dream? Every night, as darkness folds over the world and our bodies slip into rest, something strange and silent unfolds behind our closed eyes. A second life, vivid and surreal, blooms in the shadows of the mind. We fall through endless rooms, speak to people long gone, fly over landscapes that shift with thought. We dream. And though we spend nearly a third of our lives sleeping, with countless hours lost to these private theaters of the soul, we still don't truly know why dreams exist. What is their purpose? Do they serve a vital function, or are they just the echoes of a brain untethered? Dreaming is one of the oldest mysteries of consciousness. It is ancient, universal, and deeply human. Every culture has tried to make sense of it, interpreting dreams as messages from the gods, glimpses into the future, or reflections of hidden truths. We awaken, shaken, or inspired by their visions. Sometimes they comfort, sometimes they haunt, but always they seem to mean something. And yet, modern science struggles to say exactly what that something is. Despite decades of research, the purpose of dreaming, if there is one, remains unclear. We know that dreams are closely linked to sleep, particularly REM, rapid eye movement, sleep, a stage marked by brain activity nearly as intense as waking consciousness. During REM, the brain becomes wildly active while the body is paralyzed, as if nature has cut the strings to prevent us from acting out the strange narratives being generated within. Most vivid dreaming occurs in this phase, though dreams can also appear in non-REM sleep. REM cycles increase toward morning, meaning our longest and often most bizarre dreams come in those quiet hours before we wake. One of the leading theories about why we dream is that it helps with memory processing. As we sleep, the brain consolidates experiences from the day, strengthening useful connections and pruning away noise. Dreaming, in this view, is part of that sorting process, a mental rehearsal or simulation that helps encode memories, integrate them into our existing knowledge, or resolve lingering emotions. It's as if the mind is sifting through the data of the day, deciding what to keep, what to discard, and how to fit new information into the vast mosaic of who we are. Related to this is the idea that dreams help us process emotions. Some researchers believe that dreaming is the mind's way of working through unresolved feelings, grief, fear, hope, confusion. We relive events, sometimes twisted or symbolized, in a space free from consequence. In this model, dreams act like an emotional reset button, letting us feel, release, and move forward. Nightmares, while distressing, might serve to confront our anxieties in a safe container, helping us manage fear in waking life. Another theory sees dreams as a kind of virtual reality simulator. In this framework, the brain uses dreams to rehearse scenarios, facing threats, solving problems, navigating social dynamics. Evolutionarily, this could have been a survival advantage. Dreaming of danger might prepare the body to respond better to real-world threats. We practice, in the language of metaphor and distortion, for situations we've never encountered. Dreams might not reflect reality directly, but they prepare us for it. And yet, not all scientists agree that dreams have a function at all. Some believe they are simply the byproduct of neural noise, the random firing of neurons during sleep, interpreted by the brain's storytelling instincts into coherent or semi-coherent narratives. In this view, dreams don't mean anything. They're the mental equivalent of static, filtered through a projector. The brain, ever eager to find patterns and meaning, weaves a story out of scattered signals. This doesn't mean dreams aren't vivid or moving, it just means they're not designed to be. But then why do dreams so often feel meaningful? Why do they stir us, puzzle us, stay with us long after waking? Perhaps because the mind is built to search for significance. We're creatures of narrative. We see symbols in clouds, stories in silence, and dreams, disconnected from logic, unfettered by the physical, offer a playground for meaning-making. Even if they're not meant to mean anything, we find meaning in them. Sometimes a dream clarifies what we didn't know we were feeling. Sometimes it opens a door we didn't know was closed. Lucid dreams, where the dreamer becomes aware they are dreaming, add another layer of mystery. In these moments, people can sometimes control their dream environment, fly, create, explore. Lucid dreaming blurs the boundary between dream and waking, raising deep questions about consciousness and agency. How does the brain allow for self-awareness in a dream? Why do some people access it more than others? What does it say about the mind's architecture that we can, sometimes, realize the illusion from within? There are also recurring dreams, shared themes across cultures and archetypes that appear in sleep across centuries and continents. falling, being chased, arriving late, teeth crumbling. These motifs hint at a deeper structure, perhaps not just cultural but psychological. Carl Jung believed dreams tapped into a collective unconscious, a reservoir of shared symbols and instincts. Whether or not that's true, the recurrence of certain dream themes suggests common patterns in the way our minds navigate emotion, fear, desire, and change. Dreams also raise profound philosophical questions. What is the nature of reality when we dream? While dreaming, we usually believe we are awake. We accept the impossible. We invent entire worlds that vanish upon waking. If a dream can feel real while it happens, how do we know that waking life isn't another level of dream? Philosophers from Plato to Descartes to modern thinkers have grappled with this question. Dreams force us to question the nature of perception, belief, and existence itself. Children dream. Animals dream. The sleeping dog twitching beside the fire, paddling in some imagined stream, reminds us that dreaming may be ancient, woven deep into the fabric of life. If dreams occur across species, does that suggest a deep evolutionary root? What do animals dream of? Are their dreams like ours? Or are we alone in this vivid interior theater? Despite centuries of speculation and decades of research, there is no scientific consensus on why we dream. Theories abound, data accumulates, but the essence eludes us. And perhaps that is part of the magic. Dreams resist capture. They dissolve on waking, evaporate under scrutiny. They speak in riddles and move in symbols. And yet they remain one of the most universal, mysterious, and intimate parts of being alive. What is certain is that dreaming is not meaningless. Whether functional or not, it touches something deep. It reflects our minds back to us in ways waking life cannot. It shows us who we are, what we long for, what we fear, what we've hidden. It allows us to travel without moving, to grieve without judgment, to imagine without limits. Dreams are where we practice being human in ways we can't while awake. So why do we dream? The answer, for now, is not fully known, but perhaps that's not a flaw. It's an invitation. An invitation to listen, to feel, to wonder. In the quiet hours, when the world sleeps and the mind slips loose, dreams unfold their strange wings, and in their flight we glimpse something more. A secret language written in light and shadow, a reflection of the soul's deeper weather. How does the placebo effect heal without real medicine? There are moments in medicine that defy explanation. Times when healing occurs not from the chemical structure of a drug or the technique of a surgery, but from belief itself. A sugar pill, a saline injection, an inert treatment offered with confidence and care, these things, though biologically inactive, can lead to real improvements in health. Pain lessens, symptoms fade, hope returns. It is healing born from expectation. And although it has been studied for decades, the question at its heart remains unanswered. How can the mind heal the body even when the body receives nothing at all? The placebo effect begins with a simple illusion. A patient is given something they believe to be real medicine. They are told, or come to believe, that this treatment will help. And often, remarkably, it does. Their brain and body respond as if they had received actual therapy. Pain relief centers activate, stress hormones drop, immune responses shift. Measurable biological changes occur, even though the treatment is inert. This is not deception leading to imagined outcomes. It is belief, triggering genuine physiological change. One of the most studied areas of the placebo effect is in pain management. Pain is not just a physical signal, it is a perception shaped by mood, attention, and expectation. When someone believes a pill will relieve their pain, the brain often releases endorphins, natural opioids that reduce discomfort. Functional MRI scans show activation in the brain's pain-regulating areas, mirroring the patterns seen with actual drugs. It's as if belief opens a biochemical door. The body follows where the mind leads. The placebo effect has also been observed in conditions like depression, anxiety, Parkinson's disease, irritable bowel syndrome, and even immune disorders. In Parkinson's patients, simply believing they received dopamine-boosting medication can prompt the brain to release more dopamine on its own. In some clinical trials for antidepressants, placebos perform nearly as well as the actual drugs. These effects are not permanent and not universal, but they are measurable, and they challenge our understanding of healing. If a thought, a belief, can trigger real, physical changes, then what does that say about the boundaries between mind and body? Scientists have proposed various mechanisms to explain the placebo effect, but no single theory captures its full power. Expectation plays a key role. When we expect to improve, our brain begins preparing for improvement. Neural circuits adjust, hormone levels shift, and immune responses adapt. Some researchers call this the anticipatory response, the body's way of aligning itself with a predicted outcome. The brain, forecasting relief, initiates the physiological changes needed to fulfill that forecast. But expectation is only part of the story. Conditioning is another. Just as Pavlov's dogs learn to salivate at the sound of a bell, patients can learn to associate the rituals of treatment, pills, injections, white coats, with healing. Over time, the body responds to these cues, even without active ingredients. This learned response can produce real effects, especially when combined with trust, care, and ritual. The doctor-patient relationship matters. The setting matters. The words spoken matter. Healing is not just chemical, it is interpersonal. Placebos can even produce side effects, a phenomenon known as the nocebo effect. When patients expect harm or discomfort, they often experience it, even if nothing harmful is given. This shows how powerful belief can be in both directions. The mind is not simply a bystander in health, it is a participant, shaping outcomes through perception, attention, and expectation. Fear can harm, hope can heal. And in between lies a complex landscape we are only beginning to understand. Despite its power, the placebo effect is still poorly understood and often misunderstood. It is not just in your head. It is not fake or imagined. It does not mean the illness wasn't real. It means that belief, context, and perception can modulate biological processes. Placebo responses can involve neurotransmitters, hormones, immune signaling, and brain network activity. These are real systems responding in real ways to something that begins as belief. But the placebo effect also reveals a humbling truth about medicine. Not all healing comes from the molecules we prescribe. Some of it comes from meaning, from connection, from ritual and relationship. In some cases, the story we tell about the treatment is as powerful as the treatment itself. This doesn't diminish the importance of real medicine. Placebos cannot cure infections or mend broken bones, but it suggests that the experience of care is itself a form of medicine, and that the body listens not only to drugs, but to hope. This raises deep ethical questions. If belief can heal, should doctors use placebos intentionally? Should treatments be offered for their psychological benefit, even if they contain no active ingredient? Some argue this violates trust. Medicine must be based on truth. Others argue that healing should honor all paths, including those of the mind. New research into open-label placebos, where patients are told they are receiving a placebo, yet still experience benefit, suggests that deception may not be necessary. Simply participating in the ritual of care can be enough. The placebo effect also touches on something deeper, the nature of consciousness, of embodiment, of being. It suggests that the mind is not separate from the body, but deeply woven into its processes. That thought can shape tissue, that attention can mold sensation, that belief can influence biology. This is not mysticism, it is physiology, and yet it carries an almost spiritual resonance. We are beings of meaning. Our perceptions matter. Our inner life shapes our outer health. In a world where medicine is often reduced to charts and data, the placebo effect reminds us of the human dimension. It is the soft breath behind the stethoscope, the trust in a handshake, the quiet strength of being seen, heard, cared for. Healing is not only about curing, it is about connection, about feeling safe, about the deep biological relief that comes when we believe we are no longer alone. And so, the placebo effect stands as both a mystery and a message. A mystery because we still don't fully understand how it works, how something inert becomes a catalyst for change. And a message because it tells us something profound, that healing is not mechanical, it is relational, it is subjective, it is real, and it begins not just in the cells, but in the mind that holds them. Perhaps the real lesson of the placebo effect is not that belief can heal, but that belief is already part of healing, that every act of care, every gesture, every word, every breath carries within it the seeds of recovery, and that sometimes, even when the body is not yet healed, the mind can begin to whisper, "You are safe, you are healing, you are whole." Why do we age, and can aging be slowed or stopped? From the moment we are born, we begin to age. Our bodies grow, mature, and flourish, but beneath the surface, a quiet ticking begins. Skin softens, then wrinkles. Hair grays. Joints ache. Memory flickers. Systems that once danced in harmony begin to slow. And while aging is one of the most universal experiences of human life, it is also one of the least understood. We know what aging looks like. We know how it feels. We even know many of the processes involved. But we do not yet truly know why it happens, or whether, in some deeper way, it must happen at all. At the biological level, aging appears to be the gradual accumulation of damage. Cells divide and replicate, but with each copy, tiny errors sneak in. DNA becomes frayed, proteins misfold, mitochondria, the engines of our cells, begin to sputter. Telomeres, the protective caps at the ends of chromosomes, shorten with every division, like the burning wick of a candle. The immune system weakens. Inflammation quietly rises. Over time, these changes add up. The body becomes less resilient, less able to repair itself, more vulnerable to disease, decay, and death. But is aging simply wear and tear, or is it something deeper, an inherent part of life's design? Some scientists believe aging is not just a byproduct of damage, but a programmed process. That evolution, in shaping us to grow and reproduce, placed less emphasis on longevity. Once we pass on our genes, natural selection loses interest. In this view, aging is not a flaw, but a feature, a trade-off between early vitality and long-term maintenance. The body is built for survival, not immortality. Others argue that aging results from the decline of systems that once kept us young. In youth, repair mechanisms are strong. Antioxidants mop up free radicals, damaged cells are cleared away, genes are expressed with precision. But as we age, these protective systems falter. It's not just that damage accumulates, it's that our ability to fix it slows down. Aging, then, may be less about destruction and more about diminishing renewal. Still others see aging as an entropic inevitability, a slow slide toward disorder, as predicted by the second law of thermodynamics. Life fights against entropy by maintaining order, using energy to build and repair. But eventually the cost becomes too high. Systems break down, chaos creeps in, and life, so delicately balanced, begins to unravel. Despite the mystery, the search to understand aging has accelerated. Scientists now study the biology of aging not just to learn why we grow old, but to ask a provocative question: can it be slowed or even stopped? This idea, once relegated to science fiction, is now a serious area of research. And while we are far from answers, we are beginning to see glimmers of possibility. One area of focus is cellular senescence. As cells divide over time, some become damaged beyond repair and enter a state of permanent dormancy. These senescent cells no longer function properly, but they also refuse to die. Instead, they release inflammatory chemicals that harm neighboring tissue and contribute to aging diseases. Removing these zombie cells in mice has been shown to improve health and extend lifespan. Drugs called senolytics are being developed to selectively clear them, potentially delaying the effects of aging. Another target is the telomere. These caps protect chromosomes during cell division, but shorten with each replication. When they become too short, cells can no longer divide and enter senescence. Experiments that extend telomeres in mice show promising results, but also risks. Uncontrolled cell division can lead to cancer. Still, researchers hope that gentle manipulation of telomeres might one day preserve youthful function without triggering disease. Caloric restriction is another intriguing path. Animals that eat less, without malnutrition, often live longer. This appears to activate stress-responsive pathways that enhance repair and reduce metabolic damage. Molecules like resveratrol and rapamycin mimic some of these effects, slowing aging in laboratory models. The challenge is translating these findings safely to humans. What works in mice may not work the same way in the complex, layered systems of the human body. More recently, scientists have begun exploring epigenetics, the molecular switches that control gene expression. As we age, these switches become disorganized, leading to cellular confusion. Reprogramming these epigenetic markers to a more youthful state has shown stunning results in lab animals, rejuvenating tissues and restoring function. But this frontier is new and fraught with unknowns. The potential is vast, but so are the risks. Resetting the body's clock is powerful, but power, misused, can bring chaos. And then there is the role of the microbiome, the vast community of microbes that live in our gut and influence everything from digestion to immunity to mood. As we age, the balance of these microbes shifts, contributing to inflammation and disease. Restoring a youthful microbiome may prove to be another lever in the machinery of aging. But even as these possibilities unfold, the core question remains: is aging a disease to be cured, or a natural process to be honored? Some researchers argue that aging itself is the root of nearly all chronic diseases. If we can slow aging, we could delay heart disease, cancer, Alzheimer's, diabetes, all at once. This is the dream of health span, not just living longer but living better. a life of vitality that does not fade so quickly. Yet others urge caution. Aging is complex, interwoven into every aspect of biology. To intervene carelessly could disrupt the delicate equilibrium of life. There may be trade-offs we do not yet see, lengthening life at the cost of quality or causing new problems in the effort to solve old ones. And then there is the philosophical weight of it all. What does it mean to live longer? How much time is enough? What happens when lifespans stretch but meaning lags behind? Throughout history, aging has been seen not just as decline, but as transformation, a shift in rhythm, a turn of the seasons. In many cultures, old age is honored as a time of wisdom, of reflection, of spiritual depth. The slowing of the body opens space for the expansion of soul. To age is to soften, to deepen, to see the world not just with the urgency of youth, but with the stillness of perspective. Should we rush to delay this passage, or should we learn to walk it more fully? There is no easy answer. The desire to extend life is ancient. It speaks to our fear of death, our hunger for time, our refusal to say goodbye. But life is not just duration, it is presence, connection, experience. If we seek to slow aging, let it be not from fear, but from love, from the wish to live more fully, to give more generously, to see more clearly. So why do we age? We don't fully know. And can it be stopped? Perhaps not yet. But every question asked, every experiment run, brings us closer to understanding, closer to the edge of something vast. Aging is not failure. It is part of the story. But the story is not yet over, and perhaps, with time, we will learn not just how to extend our lives, but how to deepen them. Are we living in a simulation? We wake each morning to a world that feels solid and certain. We feel the weight of our bodies, the warmth of light, the softness of breath. The rules of nature hold steady. Apples fall, water flows, fire burns. The world appears consistent, coherent, and real. But every now and then, a strange question slips through the cracks of certainty, like a whisper behind the veil. What if it's not real? What if everything we see, touch, and think is part of something designed, an illusion rendered by forces beyond our comprehension? What if we're living in a simulation? The simulation hypothesis is the unsettling idea that our entire reality, every tree, cloud, person, memory, and moment, might be part of a highly advanced computer simulation created by a civilization far more technologically developed than our own. According to this view, we are not the creators of machines, we are the creations of one. Our universe would be not a vast, ancient cosmos, but a kind of program, coded and computed for reasons we cannot see. This concept gained widespread attention in the early 2000s when philosopher Nick Bostrom proposed a formal argument. He suggested that one of the following three statements must be true. 1. Civilizations like ours never reach a level of technological maturity capable of creating simulations of conscious beings. 2. Civilizations that do reach that level have no interest in running such simulation. His logic was rooted in probability. If even a single civilization could create many high-fidelity simulations of reality, the number of simulated minds would far exceed the number of original, biological ones. Statistically, then, we are more likely to be simulated than real. It's a provocative idea, but it is also deeply philosophical. There is, as of yet, no direct evidence for or against the simulation hypothesis. The universe does not glitch in obvious ways. The stars still shine, The laws of physics behave as they always have. There are no signs of the code, no visible seams in the sky. And yet, the more we understand about computation, the more the idea lingers. Because, in many ways, the universe behaves like a program. At the deepest levels of physics, reality is quantized. It comes in discrete bits, like pixels on a screen. Time, space, energy, and matter all seem to have fundamental units. Information appears to be a basic building block of the cosmos, as real as mass or energy. Some physicists speculate that the universe itself might be a kind of quantum computer, evolving from one state to another according to mathematical rules. If that's the case, could a powerful enough intelligence simulate it? Our own technology nudges the question forward. Every year, our ability to simulate reality improves. We build video games with worlds so rich and responsive that they blur the line between virtual and real. Artificial intelligence grows more human-like. Virtual reality becomes more immersive. We already simulate weather systems, economies, protein folding, and even early models of consciousness. If this progress continues, it's not hard to imagine a future where simulations of entire conscious beings are possible. And if it's possible, why wouldn't it be done? But the simulation hypothesis raises deep questions about consciousness, ethics, and meaning. If we are simulated, does that make us less real? Is experience less true if it's rendered rather than arising from a physical brain? The pain we feel, the love we share, the beauty we witness, these are real to us. Simulated or not, the inner world of experience is what defines our reality. In this way, the question of whether we are real becomes more physical than physical. If a simulated being has awareness, thought, and memory, does the origin of their world matter? There are also ethical implications. If our reality is simulated, who created it and why? Are we part of an experiment, an art project, a game? Are our creators watching us? Do they care? Or are we running in a forgotten process, one among billions? These questions echo ancient ones. The idea of a simulation is, in many ways, a modern retelling of older myths, of gods watching from above, of fate being written by unseen forces, of the world being less than it seems. The simulation hypothesis taps into something deep and timeless, the suspicion that what we see is not all there is. Skeptics point out that the hypothesis is unfalsifiable. If we are in a perfect simulation, then any attempt to prove or disprove it would also be part of the simulation. Every experiment, every result, would be controlled. In this sense, the theory sits closer to metaphysics than science. It's an intriguing possibility, but one that may lie beyond the reach of empirical investigation. Without testable predictions, it remains a thought experiment, haunting but untethered. Still, some researchers look for clues. They study the fabric of space for signs of artificiality, limits in resolution, unusual patterns, cosmic anomalies. Some suggest that physical constants like the speed of light or Planck's constant might reflect computational boundaries. Others explore quantum mechanics for signs of underlying code. Entanglement, superposition, the observer effect, these strange features of quantum theory already challenge our sense of what is real. Could they be hints that reality is being processed rather than existing independently? And then there are those who turn inward. If the external world might be a simulation, what about the inner world? Consciousness itself remains unexplained. We know how neurons fire, how brains process stimuli, but we do not know why any of it feels like anything. Why does experience exist? The mystery of consciousness is, in many ways, parallel to the mystery of the simulation. Both suggest that reality is more than it appears, that something deeper lies beneath the surface. But perhaps the most important question is not, are we in a simulation, but what do we do with the possibility? Whether real or rendered, we live in a world with beauty, suffering, complexity, and love. We form bonds, we chase meaning, we dream. These things do not vanish if the world turns out to be simulated. In fact, they might gain new weight. If reality is code, then meaning might be written into the architecture of the universe. If we are part of someone's creation, perhaps that is a call to live with more intention, not less. And if the world is real, then the same truth applies. We are still here, still wondering, still capable of shaping the world with our thoughts, our actions, our love. Simulation or not, this is the only experience we have, the only consciousness we know, the only story we are in. Whether we are players in a game or authors of our own script, the page is still blank each morning. The sun still rises, the heart still beats, and that is enough. So, are we living in a simulation? We do not know. We may never know. But the question itself opens a door. It asks us to look more closely, to pay attention, to question the obvious, to wonder not just what reality is, but what it means. In the end, perhaps the point is not to escape the illusion, but to live within it fully, awake, aware, and alive. Is there a limit to what humans can know or understand? There is something uniquely human in the act of wondering. From the first flicker of curiosity in a child's eyes to the equations scrawled on chalkboards by aging physicists, we have always asked questions that reach beyond the edges of what is known. We've mapped stars, split atoms, unraveled the code of life. And yet, as our knowledge deepens, so too does the mystery. For every answer we find, new questions bloom in its shadow, and so we are led to ask a humbler, quieter question. Is there a limit to what humans can know or understand? It is a question both practical and philosophical, rooted not just in science but in the nature of consciousness itself. Our brains, for all their complexity, are finite, made of neurons and blood, shaped by evolution. They were not designed for cosmic understanding. They were shaped to help our ancestors survive, find food, raise children, avoid danger. And yet, with these same brains, we ask about the origin of the universe, about infinity, about time, consciousness, and the fabric of reality. But are there truths so vast, so strange, so fundamentally alien, that we will never fully grasp them? One idea that touches on this possibility is known as cognitive closure, the suggestion that some aspects of reality may be permanently beyond the reach of human understanding, not because we lack the tools, but because we lack the capacity. Just as a dog cannot comprehend algebra, or a fish cannot conceive of music, perhaps there are truths that lie beyond our mental architecture. Philosopher Colin McGinn has suggested that consciousness itself may be one such mystery, that we may never understand how subjective experience arises from physical processes, because we are not equipped to perceive that connection. And this idea isn't limited to philosophy. Some physicists whisper similar doubts. Quantum mechanics, for example, is a well-tested theory that continues to defy intuitive explanation. Particles that are also waves, objects that exist in multiple states until observed, entangled particles that affect each other instantaneously across space. These are not just strange, they are, in many ways, incomprehensible. We can describe them with equations, we can predict their behavior, but we cannot picture them in the way we picture falling apples or flowing rivers. Our minds evolved in a world of medium-sized objects moving at medium speeds. The quantum world and the cosmic one plays by different rules. There is also the question of infinity. Can a finite mind truly grasp the infinite? We can say the word, we can write the symbol, but infinity is not a number, it's an idea, a horizon that recedes the closer we approach. In math, we manipulate infinities with formal rules, but conceptually, it stretches our imagination to its limits. Time without end, space without edge, quantity without boundary. Are these real things, or are they just symbols pointing at something our minds can never fully hold? And then there is consciousness itself, the mirror in which all questions arise. We think, we feel, we reflect. But where does this awareness come from? We know that brains give rise to minds, but how they do so remains a mystery. We may map every neuron, chart every impulse, and still never explain why the lights are on inside. Some suggest that this is not a failure of science, but of perspective, that the subjective cannot be reduced to the objective. Others hold out hope that a new theory, a new paradigm, will finally bridge that gap. But even then, will we truly understand it, or merely describe it? There's also the possibility that the universe itself may have boundaries that knowledge cannot cross. The speed of light limits how far we can see. The expansion of space means that some galaxies will forever remain out of reach. The beginning of time, if such a thing exists, may be hidden behind a cosmic veil, and in quantum mechanics, the Heisenberg uncertainty principle sets a hard limit on what we can know about particles' positions and momenta. So, nature may not be hiding her secrets out of cruelty, but out of structure. Still, for every argument about limits, there is a counterpoint. History is filled with beliefs that once seemed unknowable until they were known. Lightning was once the anger of gods, disease a curse, the sky a dome. And then we learned, we built instruments, we refined language, we pushed past the borders of myth and into the territory of science. If our ancestors could rise above their limits, might we do the same? Some argue that we are not stuck with the minds we have. As technology advances, we may extend our intelligence through brain-machine interfaces, artificial intelligence, or even engineered evolution. Perhaps the limits of human understanding are not the limits of understanding itself. Perhaps we will build minds greater than our own, minds that can grasp the things we cannot. But then, those minds will no longer be us, and so we must ask, is it enough for a truth to be known if no human can understand it? Even if we do face hard limits, there may still be beauty in the reaching. Perhaps the point is not to grasp every mystery, but to be shaped by the search, to ask, to wonder, to marvel. There is a quiet dignity in admitting what we do not know, in standing before the vastness of the cosmos, not in mastery, but in reverence. Some questions may not be answered. Some puzzles may not be solved, and yet, in asking them, we become more fully human. The limits of knowledge may not be walls, but mirrors, reflecting back the nature of the knower. What we cannot know may teach us who we are: fragile, curious, imperfect, alive. So, is there a limit to what we can understand? Perhaps. But maybe that's not a failure, it's a kind of grace. A reminder that mystery is not an enemy of truth, but part of it. That the unknown is not darkness, but depth. And that even in the presence of the unknowable, we can still live with wonder.